more like the connection with AstroColibri to existing platforms, telescopes, networks, BHTOM, etc. Can you switch off the sound just on this machine, because I'm hearing myself. Okay, thanks. So AstroColibri is a platform for time domain astrophysics, but it's first of all a group of people keeping it running, updating it, adding new features. All of this is currently mainly funded through the ACME project and a French grant. So we are all based in Paris-Saclay, outside Paris. And there are a lot of external collaborators who contribute features as we go along. So just as a very big overview, you know, the detection of transients through various messengers, monitoring observatories, emitting alerts about new detections, follow-up observations, classifying them, etc., etc. You probably also know most of these brokers, alert transmission platforms, the transient name server, of course, for the higher energy part, where we mainly come from, GCN. And there are now more and more of these brokers also mainly dedicated to the upcoming data stream of LSST. Quite often nowadays, to use these alerts efficiently, we have connected them automatically to our instruments. So we read, view events, JSON files transmitted through these brokers directly into the DAQ systems of the telescopes, start observations automatically. But we in AstroColibri believe that there's still an interest of the scientists being in the loop, trying to understand what's going on at any given point in time in the transient sky. The difficulty is probably clear to everybody in the room, that all of these platforms have their own data formats, their own way of communicating, be it by email, like the TNS just gives you a list of recent detections, or these machine-readable formats, or GCN circulars, where you have to read a whole human-written text. And of course, part of that is the BHTOM target list every Monday. So you can read these, but if you want to take a more active approach and follow these streams directly, it's quite difficult. And that's where AstroColibri comes in. So we listen to all of them and provide a summary in a human accessible interface. That's the main aim of our platform. Of course, we don't want to reinvent the wheel. We know that there's a huge environment and landscape of existing platforms, tools, often dedicated to certain wavelengths, to certain observatories available. And of course, we link to all of them with the advantage that if you have this centralized place where you have all the events, you can directly jump into these dedicated platforms. You don't have to copy coordinates from one place to the other. We have this direct link to the same event or the same sky region in these external platforms. And once you have all of this information in a single place, of course, you want to use that to optimize your follow-up observations. And this is then where we try to connect with an increasing list of observatories, platforms, networks, etc. And this is the main topic of Ilya's talk. All this information, again, we have the human in mind. We made it available in modern platforms. So we have a web interface that I'll show you. We have smartphone apps on both Android and iOS. I guess this is the only talk where you're now invited to take out your cell phones and hit up the AstroColibri app stores. And of course, a nice side effect of lowering this barrier of access to information about the transient sky is that now the amateur astronomers get access to this information and can participate in that science, which was very difficult beforehand. So this is a very top-level introduction, and now I want to dive a bit into a few examples, what you can do with the platform. So first of all, the web interface is running at astro-colibri.com. As mentioned, you have exactly the same functionality, just ordered a bit differently to fit smaller screens as an Android and iOS app. Feel free to search for that. And we have all the functionality provided in an open API. So if you have existing systems and you just want to interface with our database, with our archive, with our visibility plots, all these things are freely accessible. You can have a look there. There's the documentation. This page also contains a change log of our various versions and a lot of additional information like links to YouTube tutorials, etc., etc. So I'll show here mainly the web interface because it fits nicer on that screen. But again, feel free to play with the app, and if you don't find the feature you're looking for, just talk to us. So this is the main interface. If you load that up, there's an important button for you up there, which is called Science Mode. So that gets rid of the first sleeker interface that's mainly meant for the general public and amateur astronomers. So if you switch to Science Mode, you get the full access to all the features and functionalities. And then you have a few things that you can play with. You have a personalization region up there. You can create an account. Again, Ilya will talk about that. You can define your favorite follow-up observatory. You can customize how you display this map. You can even, if you're very adventurous, change the color scheme, although I don't recommend it at the moment. Then, of course, you want to exchange with your colleagues and friends. One very important way of doing is sharing a link to your selected event. So you have you found an event, a new transient, and you want to discuss that with your friends and colleagues. You don't have to remember the name and say, yeah, this was the GRB from yesterday morning, and there were 2 or 3 of them. So it's all kind of creating these confusions. You just send him the link, and if he clicks on it, either it loads the app if he's on the smartphone, or it loads the web interface, and it loads the exact same information, the exact same event. We also have a discussion forum where we discuss with our users, and the users discuss with us, and the users discuss between them, sharing observations, sharing new detections. We use that mainly to announce new releases, discuss features and bugs, etc. So there's a link to that over there. And if a given event is already discussed in the forum, this lights up, and you can dive directly into the discussion in the forum. Then, of course, you need to search for events. So first of all, you can, of course, scroll through this time-ordered list. You can also click on the events in the sky map or in this time range. So you can select the time range. For example, typically it's 1 week, but if you are interested in longer time scales, of course, you can all customize that. So if you find your very recent event in that list, you can just click on it. If you remember vaguely the name, you can just search for it. So there's an auto-completion, so you don't have to remember the exact telephone number. So it goes through all our transient and all our catalogs. If by any chance you don't find the event there's also a button where search then in Simbad, and you get the full information back as well. So that's quite helpful. Then, of course, you can do cone searches. So in this sky map, we show the recent transient phenomena, recent detections or classifications. But of course, you can also compare that to archival data, catalogs of steady sources. So for any selected event, you can click that cone search button, or you can just enter the coordinates at a random place if you want. That's very helpful, for example, to search for correlations of high energy neutrinos with flaring blazars or other sources. So this is an example where you have a high energy neutrino detected by IceCube, and then you see all the 4FGL Fermi sources in that region. In red, you see the TEFCAT sources, so TeV gamma ray sources. You see these circular things are previous neutrino detections in that region. Published by IceCube, etc. Near the galactic plane, you also have binaries and low mass and high mass X-ray binaries, for example. All of these can be switched on and switched off in these filters that I haven't mentioned so far. So we have 2 rows of filters. One, you can just select the detecting observatory of your transient. So if you're interested in Gaia, for example, you long press on this other button, and there's a list of optical observatories, including Gaia. So you get only the Gaia alerts, for example. Then, of course, you have a type of event that you can remove or add a different type of transient events that you may be interested in. If you're not interested in gravitational waves or neutrinos, you just switch them off. If you're not interested in unclassified optical transients, you can switch these off. A long press on all of these buttons opens a secondary menu where you have finer selection criteria for most of these events. A place I haven't mentioned so far, so we have all the information about the selected event on the right-hand side, where you find also some illustrations. For example, now this is an IceCube event. You see an event display of the light being detected in the IceCube detector. We add also more and more figures that put the current event into its archival context. So you see if this is a spectacular new event that sticks out of the archival distribution prominently, or if it's just a random new detection. So it's all meant to help you make an informed decision about the interest and importance of new detections and new events. Then, of course, I've mentioned this important link to external platforms, where we have a long list that you can scroll left and right to hopefully your favorite platforms. If there's something missing, just talk to us. This is only a subset of these. And again, the idea is that you jump directly into the right place in these platforms, so you don't have to search again and try to understand how this platform works, how we can select events, how we can zoom into a certain region in the sky. And then I guess most relevant for this audience, so we have, of course, the sky is dominated by optical transients. So we have all of the events from the transient name server in there, and recently we have improved the information we provide for all of them. So I go through a few examples: host galaxy information, photometry, and again a comparison with archival data. So starting by the host galaxy, so we use the WISE data to create a color diagram, where you then put the current selected event in the diagram, so it gives you a rough idea about the host galaxy. There's also a link to a much more detailed platform called BLAST that is run by friends from CIMA in the US, which has a full multi-wavelength fitting of the host galaxy information. And that's part of the external links that I just mentioned. And the next thing is light curves. So we update them daily, bringing in data from Atlas, CTF, Assassin, and if you're a member of that, a few amateur astronomer networks. So these are produced as a static image, but you can also download all the data points from all of these surveys in a common data format in a CSV file. So we create these plots, as I said, automatically for all of the recent optical transients, but you can also select that by yourself. You can create new figures at a different time range yourself, and then download the data, so you don't have to go through the APIs of these surveys yourself. That's quite useful. We also extract rough information from these light curves from each of the available filters. So we extract 3 points. This is the first measurement around the detection, the peak, and the latest measurement. So this gives you a rough idea, but it's mainly also useful for our filtering. So if you go in the detailed filter, so again a long press on these buttons, you can have a more fine-grained filtering using the features of the light curves of these events. You can search for fast or slowly rising events. You can search for events that have been observed recently, and then put a limit on the recent magnitude. So basically, filter or find events that are accessible with your possibly small telescope. So if it has been detected yesterday with a magnitude of 16, you can go for it. Everything else you can remove, for example. So this is the filtering, and then very recently we have had a nice contribution by Andrea, who is in the room, who worked with us on supernovae, where we now have a new figure again, where you compare the new event with its archival context in a plot showing the detection magnitude and the redshift. Of course, the redshift is most important. We also put a line there where you select the nearest ones, so nearest 5%, or for 1A and type 2, nearest 1%. This selection then also, for example, is available in these filters. So if you're only interested in the very brightest, very nearest ones, you can select them just by one button. And again, I didn't mention notifications. So on the smartphone app, one of the advantages is that, of course, you can get push notifications for all different types of events. And we now have a very dedicated and detailed streams for all the different types of supernovae. So if you're only interested in type 2N, then you'll get only the notification for only type 2N. So we have all these different types as a direct notification, and of course also the very prominent nearby ones just as a dedicated stream. All of this is part of the latest release that we published basically Sunday and yesterday, and should be available if you update your apps. Next step, so you have found an interesting event, you have checked that the additional information, you compared it with the archives, etc., etc. Now you want to say or check or see if it's observable by your favorite instrument. I've briefly mentioned that there's the Observatories selection, where you can select from a long list of major professional observatories, but you can of course also search for them in the IAU database. You can also enter your own coordinates, even just using the GPS position, if you have a small telescope in your backyard. And then for this given position on the ground, you get the observability figure produced automatically for all of the transients, and you can directly read off, for example, the time ranges for which an event is visible. You can call your on-site operators or shifters and let them know. So this is for one observatory. Sometimes you have access to multiple observatories. You want to see which ones of your instruments is most likely to see the event, or is best suited to see the event, or you want to coordinate observations across multiple instruments at the same time. So we have a multi-observatory visibility figure where you can select from the list of major observatories, and then you create this figure where you see as a function of time which ones can observe at a nice zenith angle or air mass. And then, so you found an event, you see that it's visible, and then of course you want to send this information directly to the telescope or to your telescope network, and this is being prepared now. We are collaborating with a bunch of observatories already. Since quite a while, we have this option where you can connect to BHTOM, for example, and again, Ilya will detail how to actually do that. Just to mention, we have expanded this integration of BHTOM to use all of the TOMs. Just so you can, if you have a TOM running or TOM toolkit running in your observatory or in your telescope, you can configure that yourself and use it directly. And then you can, from your smartphone, just push a button and the information is being ingested in your telescope operation system. That brings me to the conclusion. So we have this platform, AstroColibri, providing an overview of transient detections, all kinds of them. We have these interfaces or graphical interfaces on the web that I showed. Again, the smartphone apps, the API and the documentation is the same link, but .science at the end. I again invite you to join the discussion forum. That's also linked on this main documentation side. You can just connect to the forum with your AstroColibri account. The whole thing is running on AWS, so we don't have any outages over the last years at least. There are a few papers if you want to go more into the details that I invite you to read. And I'll stop here and I'm happy to take questions.
Thank you very much. Questions? We have some time also for the discussion. So let me start. As I understand, AstroColibri doesn't have any engine connected to built on any TOM. It's like completely independent, and you want to at this last step you are connecting it with some other existing TOM-based things, right? Tools.
Exactly. So it's our own platform, our own infrastructure, and then we just use the TOMs to send information from your smartphone to your telescope. So the TOMs will be the interface with the telescopes, basically.
But
not only the TOMs, we can also communicate by email with shifters at certain observatories because they accept TO requests by email, for example. So we have a button which then creates an email that you can just send to you. So just use the information that we already have to transmit it directly to the telescope, to the observatory, without having to copy coordinates or things like that.
But if someone has an interesting object for that person, then it's like it's connecting to, well, it's rather to contacting you or your team than to put it somewhere in AstroColibri, because it's like it's not like automatic. It's sent to all the TOMs because someone has to probably check if it's worth, right? So
exactly. So the ingestion of events into AstroColibri is automatic. So as I said, we listen to all of the transient name server and the GCNs and CBAT and all the other platforms that transmit alerts. So all the events should be there. If there's something missing or some kind of event missing, and there's a stream that we can listen to, just let us know. So you should be able to find your event in AstroColibri, and then you take the decision. I want to trigger a campaign on that. I want to submit it to PHTOM. I want to use my own telescope time. I submit it to my telescope. Right? So that's your personal decision, and everybody can do that. And you can, Ilya will explain how you can request the access to these functionalities, because I mean, not everybody has a PHTOM account, although in this room, I guess probably the percentage is high. So you need, for example, PHTOM, you need an account in PHTOM, then you enter your credentials once, and then the two systems are connected and you can submit events from one to the other.
Hi, thank you for the talk. It's a great tool. I was wondering about the properties you showed for supernova. So there are other, let's say, efforts to collect like supernova properties and so on. Are you going to merge those? So this is an addition. For example, I'm thinking of BTS, the Bright Transient server, BTS, that already provides a lot of features for supernova, for the brightest one. So are you planning on merging these, or is this an independent effort?
No, I mean, as I said, we don't want to reinvent the wheel. So I'm not a supernova person, but you just tell me where this a website is, and we can create a link to that, for example. So we don't want to duplicate the effort, right? I mean, this was just, we have the information at hand. We just wanted to illustrate it better So we were working on these new figures and filters and things like that. But if there's again, if there are new event streams, if there are new websites you typically use that we don't already have a link to, just talk to us and we add that.
So a little reminder about introducing yourself before.
Yeah. Hi, Staszek Zola, Jagiellonian University. I'm sure you are aware that there is another project with the same name, Astro Colibri, and you represent the one with bigger glass, 1 meter plus, right?
I mean, there are multiple projects called Colibri, unfortunately. I'm not aware of another Astro Colibri.
It's the same name. They have half a meter telescope.
Ah.
I believe you're going to the Almeria meeting, right?
The what meeting?
Almeria meeting, Astro Rope 25.
Maybe not, no.
There are 2 talks with the same name.
Okay, so
there are 2 projects. You have the bigger glass, right?
It's a nightmare, yeah. No, I mean I'm myself involved in a telescope in Mexico called Colibri, which does time domain follow-up of GRBs, for example. So yeah, it's a nightmare.
So maybe you should be connected to all the Colibris projects related to astronomy.
Yeah, the trademark on it.
Well, so I see Łukasz.
Łukasz Rzeczkowski, Warsaw. Can you tell us a bit more about the RAPAS you mentioned there? So what happens when you click to a target, to RAPAS? What's that? How do they react? And what happens with the data they collect?
Okay, so RAPAS is a French amateur astronomer or French-led amateur astronomer network of about 100 observers. And if you are a member of that network, you can connect to these functionalities in Astro Colibri. Then you have this button where you can submit the current target to RAPAS. This creates a post in our discussion forum. So there's a dedicated section for RAPAS follow-up. It also sends an email to the RAPAS observers. And then they collect their data in a Google Sheet. And if you are a member of the RAPAS network, you can add data from that sheet to the light curves, for example. And then you have the comparison with the amateur astronomer data, which is interesting for this community as well, because they have filters that reproduce the Gaia color response. So there are 3 different filters. So it's all started with Gaia and Gaia alerts. So we get different filters than the typical CTF Atlas filters. And the advantage is now that you have the same data then in our CSV files in the same format that you can use to plot your light curves yourself, so you can download it. So this is, for the moment, all of this is reserved to members of the RAPAS network, but they agreed that their data should be public. We have a workshop for Astro Colibri in 3 weeks' time, where we also have a hackathon. They will be there, and we'll make this connection that access to the RAPAS data are publicly available. So by the end of this year, you'll see this button where you can select Assassin, CTF, Atlas, and RAPAS. So now you know what RAPAS will be, and this data will be available.
Thank you. So I think we have to stop the questions. Thank you, Fabian. But we will continue the topic of Astro Colibri. So thank you very much.
And I have stickers. If you want stickers, just talk to me.
Yeah, with a very nice branding and color. So yeah. So the next talk about Astro Colibri and a connection to some other platforms using the example of BeachDom will be given by Ilya Jaroszewski. And I think it's already there. So yeah, I will give you.
Okay, thanks. Yes, my name is Ilya Jaroszewski. I'm a postdoc at CA in Paris-Saclay. And I will continue, as Fabian mentioned, the talk about Astro Colibri, but focusing about the interaction with other platforms and using the example of BHTOM. And for this, what you need before you can connect everything, you need a user account, and I will just guide you through how to create one and why a user account is useful. So you see the web interface. This is the non-science mode, which Fabian mentioned. You see here the personalization button, the icon with a head, or in the science mode, it's also there. And if you click on it, you see just a pop-up or a widget showing that you can log in, or if you click down here, you can create a new account. And then you see this whole form, which you have to, of course, fill out with your email address, password, and agree to the terms of usage. And then you are logged in your user account. And what you can do with it, if you click again on this personalization button, you see first something that you have to verify your email address, so that we know, or you know, that the email is in use. And if you do it, you just see your Master Colibri account, which has two sections right now, account details and request observatory access. If you go first into the account details, just to showcase what it has, is you see something where you find your user ID in it, and this is useful if you want to use the API directly via astrocolibri.science, where you will see the API connections, and it requires the user ID for identification and a controlled access to the API. So here you can copy it. Then you see some default entries in the whole web interface and app interface, which is, for example, the number of digits shown in coordinate systems and the time period shown. So the default entries are 2 significant digits and 7 days, but you can adjust it how you want to, and it will be communicated across your account on the web page and your app. And then you have something where you can put in your username and institute, which is just voluntarily there in some features which will be pasted. All right, and then you just save your settings or close the window, and everything will be updated. So one feature which you can use with a Colibri account first is the so-called watch list, where you can see on the left-hand side here the tiles for each event. And here you can see, here's this example, you see a small plus sign, which if you click on it, will add this event to your watch list. And it doesn't matter what time range you choose, or when you look at everything in the future, this event will always appear in the tile list of events, but on the bottom of it, sorted. So if you see something interesting, you can just put it on the watch list and never, and you don't have to remember the identifier name, but have it just in your tiles. So next, so now we have an event selected, it's in a watch list, so you observe it in your account. So now you want to connect it to some other platforms and possibly push it to BHTOM. And how you do it is now when you click on your the info box, and then in request observatory access, and then you see this screen here, which has some buttons. So as Fabian mentioned also, here is the RAPAS button for the RAPAS network, where you click on it, you put in a reason for your request here, and when you make the request, and we will receive a mail stating your email address, your reason for it, so why you want to join the RAPAS network, for example, because you are a member of it, and then the admins of Colibri will either approve or decline your request, and you will get a notification, and everything will be done, and you will have access. The same goes for the other ones, and this is also what Fabian mentioned. For example, for HES, CTO, LST, and Veritas, we have now dual requests ready, where you can first apply to have this access in Colibri. So just state I'm a member of HES, and then you can submit the events directly to schedule observatories, and every information that we have is then pasted in the correct forms, and then, for example, a mail is sent. BH-DOMs are found in the general category add a DOM, here indicated in red. And if you click on it, you see something like this, where you can choose a DOM from a list. So BH-DOM is already done. So if you click on BH-DOM, you see something like a login form where you log in using your username and password for BH-DOM. And what we do is we retrieve just the BH-DOM token once and connect it to the account, and never need the username and password again. So we do it safely via the token. And you don't need to send a request for it because it's some special. You just log in here and you're done. And then a BH-DOM button appears here in green, which shows everything is done, the connection is established. If it's another DOM, which Fabian mentioned, when you just click on not in list, and you get a longer form where you can create the DOM entry in our database, and this is just the information which we need. So you put it in, you put in the URL of it, it's pasted in every field. And if you are happy with how it looks, then you just create the DOM entry, and then we have it in our database, and then you can connect to it as well. So now that you are connected to a BH-DOM, in this case, this account, you can start a follow-up campaign. And here, down here, something appears, so some new text appears, and a button which states start follow-up campaigns, and click here. And if I click here, then I will see all my connected observatories or external platforms, in this case, BH-DOM. And if I click on it again for this selected source, I have to first confirm it, so I know that I didn't misclick. And when I submit it, then I will be forwarded automatically to the BH-DOM website. And this event I created yesterday, just to showcase everything. It's nothing special, so I will probably delete it. It's to show how it works when the entry is created, because it wasn't in BH-DOM yet. So the entry is created, and you see your event when as a target in BH-DOM. Now, how to find other BH-DOM follow-ups from AstroColibri is here on the top right. You have a general filters button, which is now unselected in the default mode. And if you long press on it, you see several fields which are checked. For example, here's also the distance to the sun, a parameter which you can change and select. And for follow-ups of BH-DOM, you just unselect everything what you see here. So everything else, RAPAS, HES, and so on. So that follow-up only BH-DOM remains. And when you click out of the button, the filter is applied, and you see only your watch list events, because this is only a time span of 7 days. So there were no BH-DOM events. Now, after submitting this event to BH-DOM, you see here follow-up BH-DOM. So you see that it's correctly shown in our database, and that we know that there's an entry. But I want other events, so I just extend the time range to 1st of January 2025 and see all events that were submitted from AstroColibri to BH-DOM, for example. And when I choose one event, I click on Start Follow-up Campaign. And then I have a button, I click on the button, and will be forwarded to the respective page in BH-DOM, where I have further information. And if I just scroll down, I see again a connection to AstroColibri here, and then can be forwarded again back to AstroColibri. And just to mention it, I looked at the events in the BH-DOM database and AstroColibri database. About a quarter of BH-DOM targets have an AstroColibri counterpart, and by the end of this week, we will update the Colibri database so that you will find all these events also in AstroColibri. So now I'm just clicking here on this AstroColibri link, and will be forwarded to a new instance of a web page, or if it's on the smartphone to the app, and when the event is automatically selected and I can look further into it, for example, the Colibri light curve or so on. And everything is, of course, doable in the app, where this is the interface which you see when you first open it. Here you have the menu button, and I will just guide you through it real quick. So there are no misunderstandings. When you see a menu field, you click on account, and then you have here the login form where you can create a new account or just log in. And to see the BHTOM follow-ups, here I'm just logged in because I have a general filters button on. I see only one event from my watch list, which is also has a counterpart in BHTOM. Here on the right, this field gives you the source information, so everything which you just saw on the web interface, just in a different form. And down here you have observation request, which you can click and see the BHTOM follow-up button. So yes, and this brings me to the end of my talk, where I just showed you the focusing on the interaction with other platforms, that the members of the platforms can submit your requests or data directly via AstroColibri. Because of the collaborations, we fully support the TOM toolkit, and the BHTOM connection is fully established, where you can submit targets from AstroColibri to BHTOM and link it backwards. And with this slide, I will end my presentation. Thanks.
Thank you, Ilya. You finished 2 seconds before your time ended, so perfect. Any questions? Łukasz?
That's great. Thanks. So what if you create a target in BHTOM and then I delete it for some reason, does it disappear from AstroColibri as well? Automatically?
I have to check it, but currently not.
Okay.
Because we just make a flag, but we don't check every day, for example, if it still exists or not. So if it does, we have it. If we click on it, when we just appear that it's not there anymore, and we have to discuss it, maybe update it once every, I don't know, certain time.
But also, yeah, I think you mentioned that, you know, there is many targets in BHTOM created independently, right? So they were not submitted for AstroColibri. So of course, that's more not than natural to have the link. The other way, just a note that they might have different names.
I know.
Yeah.
Thank you for mentioning it. I looked at it, and the good thing is in BHTOM you have also other name associations, and I checked all of them, and this we can do, I don't know, every month or every other timeline, and just have a script to update it.
Thank you. Yeah.
Yeah, perhaps one comment which should be made is that in AstroColibri, there's the possibility for RAPAS member to promote an object they want to be observed, a bit like Łukasz sending emails for microlensing events. In AstroColibri, you have the possibility for the amateurs to promote an object so that eventually everybody will observe them. The way the selection is made is to be discussed, but the feature exists to have several people trying to observe the same object. Yeah.
Thank you for your comment. This is also important to visit the forum, because this is also where these events will be discussed, and you will see it from the discussions also, and when the names. So this is where the RAPAS people, for example, will discuss the submission of new events.
Thank you. Thank you very much. Thank you, Ilya. Let's thank the speaker. And we continue with the next talk. It's an invited talk of Łukasz Ryżykowski from Observatory, University of Warsaw, and from NCBJ, who's going to tell us about the BHTOM and also the EASST Foundation. So Łukasz, the floor is yours.
Thank you, Milena. Thank you for this opportunity. So this is going to be a very generic and general overview talk about BHTOM. I will focus more on the technicalities and how it works on Friday morning. So if you're interested in the very technical details, then please join us for the hackathon especially the first part in the morning on Friday, where when we will go through the features and technicalities. So here, just to give you an overview, you've heard about PhDom a couple of times already, yesterday and today. I'll just start with showing some faces of people involved in this project. Most of them are here in the audience. Moritz, Chris, Fraser, Priscilla, Pavel, and Nada. So these people are here, but it's a common effort. Of course, these days you don't do things alone. There's been a lot of contributions from various people across the time. And the funding, currently, we're mostly funded through the ACME grant mentioned by Fabian before. There's some Polish funding, and we're associated with Opticon Alliance as well. So just to give you an overview of a bit of a history. This is the kind of historical slides. We started within the Opticon grant in 2012 as a small experimental section where we were exploring the time domain activities with small telescopes, and then it has grown into a larger portion of the Opticon grant. Of the Opticon, I'm sure you've heard about this, but the main role of the Opticon was to provide access to telescopes, otherwise not possible to be accessed by many people. So we've been exploring the small telescope section in that. And then in the Opticon RadioNet pilot, we've continued, and actually the current system was built within ORP around 2021 in that time frame. Now we are part of Opticon Alliance, which is not funded, but it's still there, it still exists. So hence the Opticon name keeps appearing here, and it's the legacy we still are staying within. A few words about ACME. So this is our sponsor of this workshop, so we should mention something. So ACME stands for Astrophysics Center for Multi-Messenger Studies in Europe. So as the name says, it's a multi-messenger approach to astrophysics, astroparticles, and there is loads of partners, as you see. So University of Cambridge is involved, and National Center for Nuclear Research. So these two institutes are particularly involved, and fourth in Greece as well. These three are involved in BHDOM directly within ACME. So this guarantees funding for BHDOM platform to exist and to support people working on it. But this lasts until August 2028, right? So we should keep that in mind, that it's we still have 3 years, only 3 years, or so we should think already what to do next. So this is just a comment here. So ACME goals is it provides transnational and virtual access to world-class multi-messenger research infrastructure. So that spans from neutrinos, gamma rays, cosmic rays, X-rays, radio, and there is also a part for the optical instruments. There are large telescopes involved, but in particular, we are involved in the small telescope part with BHDOM in particular. There is also centers of expertise. There is focus on the archives of the all these domains, all the spanning from optical, radio, and other wavelengths and messengers. And there's also training, like this workshop is part of the training within ACME. Okay, so but it all started with Gaia. Gaia was mentioned beautifully yesterday. So this is a Gaia spacecraft. So it has been operating for 11 years, and the main thing, it was an observatory which was scanning the whole sky, right? With the main goals mentioned by Johannes yesterday, measuring the distances and proper motions of stars, but also because it was scanning the whole sky, and the rotation period was just 6 hours. So we were able to regularly obtain data from a large portion of the sky, and eventually we were monitoring the entire sky. This is the map created by Gaia. But since we were able to monitor the whole sky within, let's say, a time frame of a day, we've built at the University of Cambridge the system called Gaia Science Alerts, which was mentioned already yesterday. And we were able to provide alerts from Gaia spacecraft. So this is an animation. So there is an updated version I don't yet have by Susanna. This is the old version, but you can see that there is always something happening on the sky, right? There's always a new object appearing. There is an object disappearing. There is a change in flux. There is a disappearance or a small rise in the magnitude. We were completely agnostic to science cases. We were just reporting on changes on the sky, photometric changes on the sky. And since Gaia had access to the entire sky, we were completely unbiased, northern galactic, the southern galactic, and including the galactic plane as well. So that made, I think that was probably the most unique transient search survey ever in history of this kind of surveys. But then we realized early on that Gaia alone is not enough to give you the interesting science out. So this is a case on the left-hand side of the Gaia data of a transient, right? You see a star having a constant brightness, and then suddenly it's going up by orders of magnitudes. So if it wasn't the network of telescopes we created for the Gaia alerts, we would have missed the science, right? So you see here, this is the follow-up, the yellow observations. They're not as good in quality, but there's a lot of them, and they are timely, right? That was important. So we were able to fill the gaps between Gaia observations, and hence we were able to extract science. In this case, this is my favorite science case. So we were able to characterize and potentially find micronetzing black holes. So hence the network had to be established to fill in the gaps. And this is the story which is applicable to all other transient surveys, LSST in particular these days. It's a new one. We'll hear about it later. But that's the thing why we need the reaction. That's why we need the follow-up. In particular, here we are talking about photometric follow-up. Okay, so and of course this applies not only to my favorite science case, but it applies to all possible science cases like supernovae, cataclysmic variables, and many others spanning, from extragalactic to solar system, all possible science cases. So this is the network, which now we call BH-TOM Telescope Network. The name BH-TOM appeared only within ORP a couple of years ago, but the network has been growing since 2013 already, and it was built for Gaia alerts. And currently it consists of 130 telescopes with very different range of sizes, spanning from 5 centimeters all the way to 2.5 meters. And you see, because Gaia was observing the whole sky, the network is also has to have the whole sky visible, both north, south, and east and west, and so on. Many of these telescopes are manually operated, but there are also some robotic telescopes, and there's a growing number of robotic telescopes, of course. Some of them are located in fairly good weather, like Hawaii or Chile, Australia, but also particularly the European part. There is a lot of European telescopes, which some of them were sitting there and having nothing to do because everyone said, okay, there's a poor weather site, why should we bother, right? But we came and we gathered these telescopes so that there is still very high need for these kind of telescopes. Even with the very patchy weather, whenever they could contribute. And the more the telescopes we have, the more observations we can collect. So many of these telescopes were actually, they are providing time, they are observing time just voluntarily. Whenever they can observe the targets. Some of them have gaps in their program, their observing programs. So that's another way of contributing. Some other telescopes, we were writing proposals, and we had some dedicated time for our BH-TOM activities. So that's a gallery of some of the telescopes involved in our network. So what are these small telescopes, right? So when we professionals, we think about telescopes, okay, so that these are mostly oldish telescopes. Some of them are very old. We have telescopes which are, like 100 years old and still operating. And some of them are new, but they are typically built in best astronomical sites in the world. But also there is this growing network of amateur astronomers, citizen scientists, we can call them. Probably that's a better word, because they have excellent instruments, right? Some of these instruments are far better than what we professionals have. Sometimes these telescopes are put in a shed in backyard, but also sometimes some of them are built in Chile or Spain. There's also schools these days, they can build telescopes, and we'll hear about one in next days. Typically, they're modern instruments, and they're actually robotized or robotic, which is great, but they have downside because they're located in big cities, so they're affected by the light pollution. And the same applies to outreach facilities globally. That there is a growing number, and there's a very high interest in equipping the outreach institutes with robotic telescopes. Very often, these telescopes are used only to show kids in the early afternoon how a telescope looks like, and then in the evening they can switch to robotic mode, and they can they can generate science while the kids are not there anymore. And then the next day, the science obtained during the last night can be shown to the kids or to a class or something like that. So this is what we're trying to do. We're trying to use the system to include all these telescopes. So the BHTOM itself, as mentioned before already, is one of the TOM toolkits, but we forked it, we expanded it, we've added a lot of new features. So essentially, but this is a web tool for coordination of the time domain observations. And when I say time domain, I mean not only transients, everything is time domain, right? Asteroids are time domain, quasars, variable stars are time domain. The main thing we have in our system, apart from automated observation requests, as mentioned by Ilya, we do process the images, right? So if there is a target of interest and someone is taking the observations, they can submit the data to our system, and the data is being taken care of, right? This is the most common bottleneck in all the operations of the follow-up facilities. And since we have 130 heterogeneous telescopes, we process the data from these different telescopes in a unified way, and hence we provide the data, and the users requesting the observations, they don't need to worry, how do I process data from that particular telescope? And then, of course, there is standardization. So what we return is the ready science-ready data. Of course, there is a lot of archives, time domain archives, and we query these like ZTF and Atlas, Assassin, and so on, because we can gain a lot of information. And as I say, we are open to new users, new telescopes, new targets. This is just a sketch. I'll show you the operation of the system. So there's some kind of a target selection, right? And Astro Colibri, that's why I wanted Astro Colibri to be presented before, because they kind of come before, right? This is the best platform I've seen for beautifully merging all possible information, also multi-messenger information, to select a target, right? The targets can come from Gaia, ZTF, Ogle, Assassin, and LSST in future. And this goes down to users, and users can decide what is their science case. For example, someone is interested in that particular quasar for 1 year, right? Or please observe the comet, right? The 3i Atlas comet every day. Or you can ask, so there is this supernova found by Gaia, we need to have it observed now. So all these requests, they can be submitted to BHTOM, either directly through BHTOM or through Astro Colibri. And this is where we take over. So we communicate with the network of telescopes. And for those who know about a little bit more about LCO, Las Cumbres Observatory, we are trying to incorporate the EON protocol to connect with the telescopes as much as possible. Especially this is valid for the robotic telescopes. So there is a growing number of telescopes incorporating LCO system, the observatory control system. So that makes all the data flow automatically, both the requests and then the data coming back to our system. So the data is coming back to BHTOM, not to the users. And then we query the archives as well. And all this data is then combined and then returned to the user. And this is essentially the science-ready data product. So these are not the images the users get. They get light curves in multiple bands. Whatever people have collected, this is what is returned to the users. And then the users can focus on publications, of course. And everything, all this can be completely scripted. That was the underlying idea of the Tom toolkit. So there is a built-in API to all possible queries, target creation, requests, observation, data processing, downloading. Everything can be scripted. Hopefully soon the publications will also be scripted. So as I said, our main feature is that we take care of all this from the image request to science-ready light curves, because we have this fully automated data processing, PSF and aperture photometry done uniformly for all 130 telescopes. And the talk by Chris Scottish just after me will explain more detail how this is possible. And then we do the standardization of observations in any filter. So we don't care which filter you have. We can actually point sometimes that your system is giving wrong filters because we can recognize the correct filter you've been observing with. And this is also valid for the amateur observers who use non-standard filters. We can also deal with that. And then the data is all downloadable. So we give the data away. It's publicly visible for registered users. This might cause some issues for some people, some communities, but I think this is the only way astronomy can operate these days. There's some examples here of the light curves. So you see different colors denote different filters, right? And these data were collected with different observatories, right? You can't tell that there is a network of telescopes contributing to these data points. It's all homogeneous. So that's the beautiful nearby supernova. That's the planet mentioned by Johannes yesterday. And the tiny blip here in March 2023 was actually the signature of the planet. Some other cases, just to show that it's not only supernovae and microlensing we do, but there's also, eruptive variables. Any type of photometrically changing objects is valid for us, right? I will stress that and emphasize this. There's been some experiments also doing simultaneous optical and radio observations of some cataclysmic variables. So there's a light curve with all the archival information, and there is some simultaneous observations in radio and in optical. Also, we've been recently testing and expanding into solar system objects, especially with this beautiful comet. You will hear more about it from Fraser. So we've collected more than 2 months of observations with the network of telescopes we have, and we built this beautiful light curve. So it is coming. This feature of non-sidereal objects in the HDOM is coming soon. We're learning how to do this on this example, but it's there. It's coming. Some statistics. At the moment, we have about 500 users registered, and there is about 400 targets requested for observations. We've processed more than 200,000 images, and this number is changing rapidly. You'll hear more from Chris about this. Typically, we process about 10,000 images every week, but recently we have increased our capacity, so we should be able to process more. So give us your data, give us more, we can handle. And there is, tens of millions of observations in the database already, because that includes the archival observations. And as I said, we invite new telescopes, new users, and new science cases. So you see, the pie chart shows the contributions of the uploads in the last 2 years. Of course, we get a lot of data from ROAD, and you will hear from Josh about this beautiful robotic telescope and LCO as well. But then the other half is actually contributed from these small portions of data contributed by different telescopes. So if it wasn't the global network, we would have only half of the pie, but we won the entire pie. Publications, there is a growing number of papers, and as I said, we cover multiple science cases. So these papers come from different flavors. So there is microlensing, of course, but there is a lot of papers, and you'll hear about these results soon. About young stellar objects, for example. There are papers on supernovae, of course, and so on. So far, there is more than 20 papers already published. But the main thing I want to emphasize that we include all the observers. Everyone who has contributed to a given target, which ended up in a publication, we invite everyone to be a co-author of the paper, which for some observers, like school pupils, it's quite exciting, right? We have papers with school pupils as co-authors. So this is the currency, let's say, we pay people back for their contributions to the observations. You'll hear more about this particular paper, but I just wanted to highlight that we've also observed the T Corona borealis, and it's not going to explode anytime soon, unfortunately. Right. So just a few words towards the end about the East Foundation. So it's been hovering in my mind and other minds for quite a while, that the things we do with BHTOM can also be expanded towards citizen scientists, in particular people with small telescopes, right? And we thought, okay, how can we incorporate them into the broader picture of science we do with BHTOM? So the foundation was an idea to establish it and move these activities around BHTOM towards citizen science through the foundation. So we use BHTOM as the core tool, but we make this usable by non-professionals, right? So people not exactly familiar with complex scientific tools and scientific understanding. So we're involved in outreach and educational activities through that, and we connect professional astronomers and amateurs. So both ways, actually, we give professionals the access to amateur observers and amateurs access to real science. So the amateurs, instead of taking yet another image of M31 with a beautiful telescope, they can take a boring-looking image of a blazar or of a supernova, but then it is then converted into some science. So for many amateurs, it's groundbreaking, and they can move on. They can change and upgrade their activities, and they can learn through that as well. And of course, we're thinking about expanding the telescope network with new telescopes, but also we work on the technical expansions, and so enhancing the telescope and data processing technology. And protecting dark skies is one of the important factors of the foundation as well, because we work with amateurs who are severely affected by the light pollution. And our motto is where the sky begins, because you see the game here. So east, right? Like east, the direction, but double S. So where the sky begins at east, you get it? Yeah. Okay, good. So you can become our partner. So you can join the telescope network, and we'll provide the technical support. We'll include the partners into scientific publications, and then we will apply for projects and grants. And we already received a couple of interesting grants, mostly from Polish government so far, with our partners. And of course, we welcome schools, outreach institutions, amateur astronomers, associations of amateur astronomers to join us. We also have positions of ambassadors, and one of the ambassadors is sitting here for Lithuania, Edita. The role of ambassadors is to essentially communicate the activities of the foundation within their local environment, in particular in the local language and local culture. So that's what we found quite important. You'll hear from Suleiman as well online later how does work, how this spreads in Turkey, for example, because we found that the language barrier is often quite an important thing to overcome. So the ambassadors are there to help and spread the word. We have a lot of scientific partners. I just listed the most important ones below. As I said, we have some funding. We're looking for funding. We got some funding from the Polish Ministry of Education already. As I said, BHTOM is still funded through the European grant, but that's not going to last forever. That's why we're looking for other opportunities. We've applied for Erasmus Plus projects, so everything kind of outreach related with the use of small telescopes and BHTOM as the core is in focus of our applications. But of course, we're looking for sponsors everywhere. I'll just finish with the list of workshops. I mentioned that in the introductory talk yesterday. We started in 2010 in Cambridge, and then we actually had the workshops essentially every year, except one which was online in 2020 for obvious reasons. And now we are at the 16th one. So I think this has built the very nice community. I'm very happy to see you all here. And I hope it will continue in next years. This community of telescopes, small telescopes contributing to science, and then using the small telescopes into scientific applications. So thank you.
Thank you, Łukasz, for the talk and also for making the idea of this conference happen for the 16th time. Any questions to Łukasz? Let's see, there was hands? No. Yeah.
Konstanty Sidlacka, German Center for Astrophysics. So you mentioned that the funding is now secured till 2028. Do you already have some ideas what happens next? Because the people who would join now would like to know if this is only for a few years, or is there a plan? I hope that would be longer.
Well, I'm open to ideas, right? And we'll be looking for the ideas to support it. But I think this is such a great idea that the funding agencies would be silly not to support it. But you never know. Of course, we will be looking for funding, right? So for now, we're secured, but that's why we're trying to look for some independent sources of funding, for example, through the foundation as well, and then expanding to other ways to keep it running, right? Even if the European funding is over, we hope to continue with other sources of funding, for sure. Yeah, so please do join.
Yeah.
Yes, my question is to clarify your point. When you submit an image to your system, you are doing the photometry automatically, but to do that, you assume that you have some calibrating stars in the same filters within the same field of view, right?
Exactly.
Which is not always the case.
Well, we use Gaia. Gaia has observed the whole sky. We use Gaia catalog as the catalog of standards, right? So we standardize regarding to the field stars we see in the same image as obtained by Gaia. So that's our standard. So we don't do the classical going to the standards and observe the standard and then go back. We use the stars we see in the same field as our target, as standards. It works. Well, okay.
I have one short question here.
Are you focused exclusively on photometric data, or are there some of the instruments that provide, for example, spectroscopy?
Yeah, I always get this question. We've been thinking about, and we keep thinking about spectroscopy time domain. It's not as, well, it's way more complex, right? So processing automatically the spectroscopic data is the main challenge here. I know that there are attempts to do it automatically, but since our goal is to take care of the bottleneck in the data processing, photometry is still the simplest. But if we have telescopes with spectroscopic capabilities, but we're not able to process their data yet. I'm really looking for, if you have any ideas, so it would be great to have that built in, but that's not so straightforward. Mm-hmm.
Thank you. Let's thank Łukasz for the talk.
Yep.
And we continue with the last talk before the coffee break. It's also about BHDOM and photometry that will be given by Chris Scottish. And yeah, hope it works.
Hello everyone, my name is Chris Scottish and I'm from University of Wrocław, where I'm a PhD student, but I'm also affiliated with University of Warsaw, where I work on BHDOM, mainly on the part of the behind the scenes, which is the CCD thought pipeline for processing all the data that you upload to BHDOM. This is work done by me also and Przemek, who unfortunately couldn't be here, but he's also working very hard, even right now in Wrocław. We are adding all new features all the time. So stay tuned for the newest version of the pipeline. But in this talk, I would like to present to you the general idea of how the CCD works and what has been done in the recent year to improve it. So CCD is mainly the pipeline for processing FITS images, which is both straightforward, but also not so an easy task if you have to do it for more than 150 observatories, which each have different instruments, different telescopes, different cameras. So this is a very robust task to do it in a very homogeneous way. So what CCD does is basically, first of all, we try to assess if the FITS is even processable, because we also get some FITS files that should not be even uploaded, but that's the thing with robotized telescopes. We also get some data that is not useful. So we do some FITS assessment, of course, astrometry, and then photometry. Astrometry is done with the Gaia DR3, so the most reliable source right now that is available for astrometry. We also right now have very well established monitoring process for all of the processing. Also, we are, as I said before, we are adding new features for users to see on which step of the processing right now their FITS files are. So if you go to the BHTOM website and see your data, you can see that there are some new additions already. There are some new fields that you can explore, but still all of those features will be added very soon. Also, what I need to mention that also it works like a black box. So it's very this name, this shortcut, the GIGO means garbage in, garbage out. So if you put low quality data in, you will get low quality photometry. So this is basically this kind of obvious that I need to state it. So CCD, of course, works with BHTOM. But also it's a standalone software. If it can be installed on almost every machine right now, because what has been done that this default pipeline is now Dockerized. So all of the software that is listed here, some of it is quite old but still very reliable, like Dawafot, Sextractor. And also some additional software that is also available or our own scripts that we developed for enhancing the processing process. So all of it is Dockerized, so it's more or less independent of the machine that you are running it on. But also what has been done during the recent year, because last year on a CRIT meeting we had it Dockerized, but the pipeline was working in a kind of single file process, so it was still a lot of work to do. But during these conferences we get a lot of ideas, and I need to mention the guys from Zielona Góra who gave us some hint about how we can make our pipeline work better with Prefect, which is kind of a software that I will talk to you in a minute. But first of all, I also need to tell you about why we chose Docker. Why is it Dockerized? Because, as I said, it can work on almost every machine that you can think of. Because all of the specific versions of the Python packages, all the software that is inside needs to be run independently of which machine you have. So right now with Docker, we have consistent runtime environment, so results are also consistent. There is an easy installation script which can do it in a few minutes. You can install this default on your machine. And also this is also a step for scalability and a step for moving the whole process of processing data possibly in the future into the cloud. So this might be also one of the milestones for CD4. So coming back to Prefect, what is a Prefect? So Prefect is a software that is kind of an orchestration engine that turns all of the functions that we have in our pipeline into a very well constructed product, which gives us very useful things such as ready-to-go API that we can use to trigger the processing. We didn't have to invent it ourselves. It was already there. We can also schedule workflows and manage queues and concurrencies. So in the past, when we were flooded with data, it was kind of difficult to manage it because we had limited processing capabilities and limited monitoring of the whole process. So when you were uploading data, you could get a lot of errors. We had to manually restart it. We had to go through each feeds file and manually and assess if it's worth reloading or not. And right now, all of that is automatized. So a lot of work that we were doing manually is not there anymore. So it also comes with a really nice GUI where you can see all of the processes. All the green ones are all the feeds files processed. This is a screenshot from the 8-hour period. You can see there is over 1,000 images processed. The blue ones are currently processing, and the red ones, which are only a few of them, are the ones that gave errors, and those errors are simply due to they were just feeds files that were not processable because no stars were detected on those feeds files. So this is very, very encouraging to see that it works really well. So just to go through, quickly go through steps of CD4 workflow. So we start with the standardization of the feeds headers alongside with the assessment of the feeds file quality. Then we do the astrometry with Gaia DR3. Then we use DAOPHOT and Sextractor for photometry and estimating all the necessary parameters for the stars in the field. Also, then there is an automatic selection of the PSF of the stars for the PSF photometry. So this is for the profile photometry. So this is the step that is already working quite well, but we are still working on improving that step. So we get even more precise, even better photometry and profile photometry for more files that you provide. So when the end result is an ASCII file with photometry and astrometry, which is available on the BHTOM website to download. But as I said, we are still working on improving, and pretty soon you will be able to download all of the photometry that is provided with the CCZ-PHOT. So all of the aperture photometry, all of the profile photometry, also different kinds of different variations of those photometries, and we will assess which photometry is the best. So with this one will go to the calibration server, but you will be able to download all of the instrumental photometry that is produced by CCD-PHOT. Also, as Łukasz said, we are working very hard on adding the new features, such as searching for non-catalog objects. So the support for non-sidereal objects for CCD-PHOT and BHTOM is underway, and it will be added pretty soon. I think it will not be. It needs a lot of testing right now, so we need to assess if this is done in a way that works works well for all of the files that you will provide. Okay. And as you can see on the right side, there's another screenshot from the Prefect server that gives us this nice graphical view of how all the processes work, how they are connected, and we can easily monitor if something goes wrong. We also have access to the log files. And as I said, the API is available for that, so we can also parse all of this information via API. So this can be linked with BHTOM, and all of the statuses that are produced by Prefect, they can be available in BHTOM. So I would like to present you with some examples of some results. I prepared 3 slides for that. First one is moderately dense field, but it's not so straightforward because we see there is some nebula present in that. This is from the Road Observatory, so the quality of data is really good. And as you can see on the right side, on the right-hand side, you can see the image with all of the stars that were detected and then subtracted from the image. So the profile photometry step went smoothly, and you can see that all that's left on the image is just the nebula, and all of the stars present are calculated. I can also show you some picture with slightly worse quality. This is actually from Adimayan telescope, but you can see that there were some problems with calibration. You can see some artifacts on this image, but still those kind of images will get processed, and the photometry will also be valid for them. There might be slightly higher error bars, but still the photometry will be good. And the last example of more dense field, which is the dense fields are of course the most are most challenging because they are also time consuming in terms of computing time, but also with a lot of blending and a lot of stars in the field, you can get some errors that I will try to get into detail on Friday on the hackathon. But you can see that even this kind of dense field is still well subtracted. Okay, so my last slide is this graph that I want to show you how many FITS files we were processing. It starts in June 2024 and ends this last week. This last bar is from the last newsletter, so we can see how many images were processed and how many were successful, which is the blue bars. The gray bars are how many were processed, and the orange line shows the success rate. So how many errors, how many how many FITS files without errors were processed. So we can see some variations here. You can see the effect of the workshop, which is the October 2024. You can see the rise after the last CRIT workshop, the rise of the images uploaded. Actually, the 16,000 one is from TCRB, which is very easy to process field because it's very sparse field. So we can see that we process them a lot, but then we see a slight decay of the images processed weekly because of limiting computing power, and also basically it's the effect of the limiting computing power. So what I need to mention that we recently activated our new processing server in Warsaw, which has very high capability of processing a lot of images weekly, and we estimate that we can at least 15,000 images during the week is possible for that. You can see this last two bars are from the last 2 weeks. So this kind of trend will be right now constant. Each week we will process at least 15,000 images. We are trying to achieve 100,000 images a month. So this is the goal. I think it's possible. And I would like to leave you with the contact information and the motto for the CC which is no feet left behind.
Thank you very much. We have time for one short question. Fraser.
Fraser Gillen, NCBJ. So it was a really cool talk. Thanks. I was wondering, for your aperture photometry, how do you go about picking like an aperture? Do you base it on the full width half max? So for example, some objects will change size on the sky. If you look at like a very active comet, for example, or maybe some kind of stellar object. Is it like a one aperture fits all, or do you base it on something?
The aperture is changing. We do it dynamically.
Okay.
Okay, I think Chris is here. We are over time, so I can find him over the coffee break. And thank you, Krzysztof. Thanks a lot. And yeah, few announcements.
Okay. A few announcements from the log, and we'd like to show you already. So a few things. First of all, yeah, this is coming. This is coming. So a few announcements from the log. First of all, thank you everyone who has already uploaded the slides for the next session, and whoever is uploading in due time. It makes our life much easier on the log table. So please continue uploading. Then the program has changed. In the next session, the last 3 talks will be given after lunch, and the first 3 talks from after lunch will be given before lunch. An updated program is printed on the desk. And we have a bit of paperwork. So that's why we are showing here the webcam from Tenerife. In the back you see Teda. This is how it looks up there right now. We are above the clouds. So we have 59 people registered for the tour, and the bus can take 54. So experience has shown that some people opt in and then opt out. So in order to give everyone the experience they want, if you have decided to not go up, we would ask you to fill out the sheet at the log table just to cross your name out. And to give everyone the experience, if you have a car, please come speak to the log in order to that we can perhaps arrange with some car drivers. It's basically one car. We have 4 excess people. Another thing, it might look sunny and nice. Don't get fooled. The temperature up there is something like 10 degrees. So please bring a jacket, a good jacket and a pullover, because we are going to stay up there till the sunset. And then when it's even get more chilly. It can get windy, but we're at 2,500 meters, so UV radiation is pretty intense. Please bring also a sunscreen 50 or better. It's just we went up, we were sunscreen and we didn't refresh, and we got sunburned. So take it careful, take it serious, please. This is one of the telescopes we're going to visit, but more than tomorrow and on the way up. Yeah, please bring clothes, and if you have good shoes, bring them as well. Then, just after lunch, we're having the tours through the IC labs. We have 40 people who registered. This number is fixed by the number of clean suits that they are having. Just at 10 minutes past 1, be ready outside at the blue barrier. The IRC team will come and kidnap you, as they phrased it, and take you down into the catacombs, the clean room. So please be ready. Lunch is starting at 12:30. Please be ready at 10 past 1 to go into the clean room. Then we also have the hackathon. We also have a list at the log table where if you're opting out, please just cross your name by today. And I would, in the afternoon, please do so before lunch, because I will take the list to ISC in the afternoon and communicate how many people they have to expect. And, oh yeah, and by the way, we were informed by the ISC Tech that we need to check in. So we prepared a participant list, which will be available at the log table. So every time you come in, please just search for a name and put your signature or initials there so that they know that in case of emergency, who has been here today. So we ask you for your collaboration, and now enjoy your coffee break. Thank you.
Ja rozebrał.
Będziesz stała przy stoliczku? No tak. No, chcesz się powiesz, bo ja mi telefon będę pisał. Tak, zasób to jest. Będziesz tak schowany.
Ah, yes. Found it. Miłosz, I found it.
Hello, Lukasz. This is Josh.
Hi, Josh.
I will check your presentation via the YouTube channel.
Okay.
I was not.
Welcome everyone after the break. Could I ask the speakers to join us in the front? So the next talk is given by Miłosz Pruszyński and Jakub Nurkiewicz about the development of the universal SNR estimator within the framework of BHTOM. So yeah, the floor is yours.
Yeah, hello everyone, and thank you for invitation. It was okay. Hello everyone. It was thank you for invitation, and it was great to listen to all the talks previously. So my name is Miłosz Pruszyński. I'm a member of Astrophysics Student Research Club at Gdańsk University of Technology. I'm studying mechanical engineering. Not really many common grounds with astronomy, but well, it's kind of a hobby of mine. Okay, so our task was to develop a workflow framework of estimating SNR values for astronomical observation sessions for BHTOM project. And there are many challenges associated with it, as the gear is really varied. It's not standardized. Everyone is using different type of devices, different filters, and the problems such as quantum efficiency curves is also different for each camera. So yeah, this is our opponent. It's SNR equation, and it looks quite harmless, but yeah, that's the dependencies that we are facing. There is quite a few parameters. So yeah, our first idea was to use a fully deterministic approach to calculate everything from to digitalize curves, then later to multiply those by transmission of filters, later by atmosphere extinction curve, and so on. But as you may imagine, it was not really good solution because the many cameras are exotic, are small batches cameras with private documentation, that's data sheets. So we couldn't access QA curves for many of those. And additionally, it's really not the best idea to scale automatic digitalization because it tends to produce, well, not very best outcomes and results. And also, like, fully deterministic approach will be resulting in, it cannot be deterministic for the whole length of the process. There are multiple factors, such as, for example, coatings on mirrors or lenses that are also dependent by the wavelength, and you cannot find those very easily. And in many cases, even people that are using those telescopes don't really know what they have because those are, as previously said on the presentation, often very old devices. So Machine learning was our solution for this problem. So okay, let's remove from this slide all the duplicates. And it looks quite nice right now. And yeah, so what kind of variables are affecting our SNR? Those are weather dependent variables, gear dependent variables, target dependent variables, and location of the observatory and coordinates of the targets dependent variables. So yeah, some of those are really not very handy, speaking of the whole Beachstone project, because we cannot really predict few days in advance what kind of weather there will be in some place when we are planning the observation station. And so from the start, we just had to, resign from some of those parameters. On the green, in a green rectangle, you can see the parameters that we thought are useful and pretty easy to access or derive from other data. So yeah, for example, pixel scale is derived, F value, aperture, and air mass, moon target separation, sun altitude, moon altitude, moon phase, sectant of a zenith, etc., etc. We are using as an SNR Mach error that is inverted, because it's the same thing. SNR inverted is Mach error. And we are using also readout speed as an indicator for the machine learning algorithm to learn if the camera is CCD or CMOS. We haven't really extensively tested it right now, but our hope is generally that algorithm can learn the difference between the CCD and CMOS from the readout speed, as it's often varies from between different types. All right, so our final idea was to use machine learning, and Jakub Nurkiewicz will take a microphone from now. Thank you.
So I am student of the informatics at the Faculty of Electronic and Telecommunication and Informatics, on the Gdańsk University of Technology, like the Miłosz. And now we have the structured data set, so we can start modeling. Our first attempt was to utilize the deep neural networks. It was like using the cannon to kill the mosquito, but this approach have a problem because we don't have so much varied data in data set. So we moved to the more classical machine learning methods, like the random tree regressor. The random tree was not so good choice because it tends to fast overtrained. And at the end, we have tried the random forest regressor, which at that time gives the most appropriate results. So I will tell you how it works. So our test data set includes the LCO GT observatories like Gaia. We can see that more than 71% of data have a relative error below the 20%, so it can be used in production. But there was one big issue. We can see that the results are pretty good, but if we see at the graph predicted SNR versus X time, we can see that our model is not handling the relationship between the exposure time and SNR so well. We don't have the root square line. We have something weird, and it was caused due to the fact that we have a lack of possible exposure time in our training data set. And also the resolution of the SNR was so low because SNR was the reverse of Mach error. We have only 1000 possible MAC error values. When we reverse it, we get also only 1000 possible values, and also model tends to the overfit. And what we do to fix that problems, we created the new target variable. We divided the SNR by the square root of the exposure time. We get more than the 20 times more target variables. And now the SNR without X is mostly independent from X time, which led the model to utilize also values like the moon phase. And as we can see, now the graph of the predicted SNR versus exposure time is correct. So there are the results for our last approach. We can see that the RMSE is slightly worse than before, but now the R2 coefficient is higher, so our model is more linear. And also our model now have better extrapolation and interpolation. So let's talk about the possible methods of improving our model.
Yeah, so there are a few things that we can improve in the model. And one of those things is using more varied data. For example, varied in terms of exposure times, because this approximation that we are using with the square root, it's not the best, it's not working the best. Let's just say it would be better to use normal and real data. And of course, we would also appreciate more failure data to let the model learn what cirrus clouds are doing to the data. Maybe not cirrus because we are not using weather as of right now, but for example, what target close to the moon is doing to the data, for example. And we could use also a calibration model, calibration constant, because we observed that in many cases that where observatories is not in the dataset, training dataset. And we can apply a simple multiplication to get the results good for this observatory. So that's one way of doing it. And the second one is making a new model that will be specifically trained to translate the general model results for each observatory. So it would fit better. And well, thank you for your attention. I think we lost one slide with our LinkedIn's. I think we're gonna have to deal without it. We'll live without it. And just checking if it's somewhere there. Yeah, it's nowhere. And thank you so much for your attention. And our mail is yeah, maybe on a coffee break we will tell you our contacts because it's not working right now. Thank you so much.
Thank you very much. Thank you for being perfectly in time, and congratulations on the work that you do. Actually, not being astronomers and doing that as a passionate. Do you have any questions to Miłosz and Jakub? Any comments? Yeah, Łukasz.
So you tested it on LCO data, right? How easy it is to employ and use other? Have you looked into other observatories as well?
Yeah, generally speaking, it's a same format of data that is used on BHTOM because we were training it and making a data sets for training just with the BHTOM data. Like we are, if its main use case is BHTOM, we have to deal with the data that is available. So it wouldn't be any problem. And we previously tested other observatories, and generally speaking, if the observatory is in data set, it's pretty good. But of course, we can imagine with a lot more data, maybe applying more deterministic values, for example. So maybe we could estimate a background flags with moon phase, etc. And it could be maybe we could even lift those results even better with a lot more data from different observatories and training time. we could get much better results. But from the data we have used, I think it's pretty good result. Thank you.
Thank you. So I was wondering, the idea is to have it inside the BHTOM, this kind of tool, right? As an integral part of the that you can calculate your exposure time based on SNR within BHTOM, right?
Yeah, like for the planning of observation campaigns, for example, we have some supernova. We have to assign this observation to, I don't know, 6 observatories around the world, and we don't want to waste time for testing different exposures, for making more frames than we need and longer than we need in SNR that is too high for us. So yeah, it's optimizing the whole process and time utilization. Thank you.
Thank you very much. So yeah, thanks a lot. Let's thank the speaker. Thank you.
I have a question.
Oh, sorry. So there was a question from Zoom.
Yep.
Yes. Hi, I'm Josh Hamsch, operating Road Observatory, and I am also wondering why you have taken LCOGT, because Road Observatory has probably twice the number of submissions to BHTOM than LCOGT. And I'm observing at any moment when the weather is good, and the weather in Chile is always good. So also close to the moon and with full moon up. So it would be very nice to see how my images are compared to, for instance, LCOGT.
Yeah, I mean, it's because of, I think it was a decision of Nurek. Nurek, if you would like to take it from now.
Okay, we chose it because we are now on the Tenerife, where there is the observatory, which is in this group. So we choose to check something local.
Okay. Okay.
No problem. The next step could be road. Thank you very much. Thank you, Josh, for the question. Let's thank the speakers once again. And let's invite next speakers. The next step gonna be delivered by Piotr Hofbauer and Barbara Joachimczuk. It's gonna be about electronic observational log for optical telescopes at the Observatory in Piwnice. So the floor is yours.
Hello, everyone. My name is Barbara Joachimczuk.
And I'm Piotr Hofbauer.
And we are students from Nicolaus Copernicus University in Toruń, and we wanted to tell you something about a project of ours that we have been working on for the past couple of months, which is the electronic observational log for our domes in Observatory in Piwnice. So the main idea behind the whole project is that currently for logging in our telescopes, we are using Excel spreadsheets, which is a technological improvement from a notebook. So we thought that maybe we could do something better. So the problems we wanted to solve was mainly the problem with data that was kind of forgotten and it was laying around on the computers, and the observers were too busy to upload it or calibrate it. And there were some inconsistent notations in logs. Everyone was doing it differently on their own way. There were difficulties with finding the EUROS object data. So first you had to go to the Excel spreadsheet and then Control F it and see when it was observed, and go to the files, find it in the files. And then maybe there was no flat fields made. So you had to go and find nearest flat fields. So it was taking a lot of time, and we thought that maybe we could do something simpler. So our solution is a one system that is for logging, integrating, calibrating, and uploading the data. The workflow is very simple. So during the night, the observer is observing, and that's all they have to do. During the day, the data is integrated on our server, Then it's run through Python scripts, and then it is ready to upload or just to do some science with it.
Okay, and let's look at the bigger picture, if I can have the remote. We have our 3 telescopes, and according to the policy of our IT department, the data is synchronized once a day, like afternoon, and it goes to the central storage in our server room. We were also provided with the server on which we've implemented Astrolog. And when Astrolog has a connection to the storage, and when it detects the new data, it starts to process it. We've implemented a web application for users to access it easily. It's well, the best choice as the BHTOM because it works. You only need a browser, so it doesn't matter the system you have. It's also responsive, so it works on phone, tablet. No matter what computer you have, you only need a browser to access it. And to Astrolog, we've also plugged some IoT things like the weather station. So no more manual inputting weather conditions like humidity or the temperature or like clouds.
And what happens with the FITS files is very simple. We are using open source libraries to process it. So it's the reduction process is happening with cctprods. And the astrometry is happening, the plates are solved with astrometry.net, and also the air mass is calculated based on the data from astrometry. Then we are using simple AstroPy to get the metadata of the observations, like how many pictures of what objects were taken, in what filters, binning, subframe, and then it's shown on the web application, and then the data, if it's an object in BHTOM, it gets uploaded to BHTOM.
Yeah, and let's talk a little bit about this web application because that's the core feature of all of the system. And let's talk only about the most important features of this web application, which is, of course, data browser. So no more need to manually go through all those folders and look for your data. Meteor data lookups, so you can check the current weather conditions without opening additional cards in your browser where you can eventually get lost in your cards. Observatory status messages, I will talk about it in a minute because it's easier to understand when we see it. Observation management, so the only card in this system that observer will actually work with, and the jobs lookup to see what the system is actually doing. So here we see what I mean by observatory messages in panel that is called notices. Those are messages, warnings, or critical errors to notify observers what is happening at the observatory. So for example, that the telescope is not working, or we have a poor tracking, or another one, because those messages weren't always passed to all the observers. So now when observer starts to do their job, they see those notices on the homepage. We also have the request panel, so what our science team actually needs right now. If there are no needs, if there are no needs or there are less objects, then we also integrate the newsletter from the BHTOM for our observatory. And that's the card that the observer will actually work with. So they will only input who is observing. There can be multiple observers because some people might be learning, so students. And only comments. So comments for a specific object or comment for a night. Here we have our data browser. It works in 2 modes. The first mode is date. So we see only observations, and second is objects where we will see objects. And we can sort it, we can filter it, sorry. We can filter it by the range, objects, filters, observers, and telescopes. Depending on what you click at what record in the browser, the according page will open. So we have.
So here we have an object page. We have an example feeds that was taken. We have visibility chart for the current time. And we have the time when the object was observed, some metadata, the calibration images if were taken. The user can download all the data if they want, raw or calibrated, because everyone has their own philosophy sometimes of data reduction, and also to download the calibration files from the night.
Yeah, and that's the view of the night itself. So not the object, but the night. So we see who was observing, what were the comments for this night. So for example, there was a strong wind and boars appeared near the dome. And in the middle panel, when you select the object, the right one opens and you can see specific comments about this object and what images were taken. When you click on the specific image series, then additional overlay will open with more specific informations like beaming, CCD temperature, and so on. And that's the jobs page where we can see what the system is actually doing. So is it during the calibration, or is it copying files, or is it uploading to BHTOM? And we can see if some jobs have problems. If they have, the additional button appears details, where in additional overlay we can select alternative tasks, what to do with this error to get rid of it.
So for the future plans, we need to solve problems with authentication system and user management, because, for example, if a data is uploaded somewhere, it needs to be uploaded with the author, with the correct author, and then it needs to use the correct token, and the token needs to be stored somewhere. So it's also a problem that we need to solve. We also want to do Nina integration, because one of our DOMs is currently being automated, and the Nina is a powerful open source tool. We are also thinking about doing possibility of excluding a frame doing acquisition if the observer sees that there was like a huge satellite or something wrong with the picture, to exclude it from further processing, and to integrate more external sources.
Yeah, right now it's Simbat and BHTOM, so those are our external sources, but we plan to implement more catalogs and well, other systems. And of course UI tweaks, because that's version 1, and we will see from the feedback from users what to change, because there will be things to change.
Yes, and that's our project. Feel free to contact us if you have any questions or ideas, because it is in development. And thank you for your time.
Thank you, Barbara and Piotrek. Do you have any questions? Here?
At what stage are you right now, and when you are planning to launch it finally?
So we are technically we are in testing stage, because we've finished things in development, but we are waiting for our IT department to finish the server room, because it takes a little bit long for them. So it's in a testing stage.
Any more questions? Here.
So what requirements does a system have to be integrated in your system? And could it be also used for other observatories and not just your observatories that you have?
So right now we plan to make it more general. So we aim for also for other observatories, but because it's the first launch, there are some specific things only for our observatory. But if tests are passed, like they will be successful, and the feedback will be positive, then we'll make those dedicated things more general also for other observatories. So if someone wants also to test it, feel free to contact us. We'll try to figure something out.
And is it working for like all telescopes at the observatories? Now is it prepared like that, or just for one? Or because in PNITA there are like more telescopes, right?
So we have 3 telescopes, and right now the telescope doesn't matter, because we still use MaximDL and you can't integrate it with anything. So our observations are like manual. So the things that the astrolog gathers is only from the FITS headers,
and the telescope doesn't matter. The parameters of the telescope you input manually on the configuration pages of the astrolog.
And what about radio telescopes?
Yeah, in plans.
Oh, great. Thank you very much. Congratulations. Yeah. And now we are moving smooth from the tools to the user cases. And as you know, there is the change in the plan. And the updated plan is on the web page. And the next speaker, it's Sofia Nagy. That's going to tell us about young stars and accretion variability results from Gaia science alerts. Yeah, the floor is yours.
Okay, thank you. Yeah. Good morning. So I'm Zsófia Nagy from Concoli Observatory, and I will give you some updates on accretion variability in young stars and some results from the Gaia science alerts. And I'm going to be speaking on behalf of our collaboration, GLORIOUS, which stands for Gaia Science Alerts to Find Eruptive Young Stellar Objects. So our goal is to study the variability of young stellar objects, which actually is quite complex, as this figure shows. It occurs on many different timescales and amplitudes, timescales from about day through months, years, up to decades, and even centuries. And there are some variations below 1 magnitude, but there are also variations with much larger amplitudes. And also the processes that contribute to this are quite complex. However, they are mostly related to either changes in the accretion rate or in circumstellar extinction. So I'm trying to find targets where the variability is due to change in the accretion rate. And I'm studying large amplitude variability, so-called episodic accretion. And the examples of episodic accretion are eruptive young stars. And why we care about this? We think that this may be a common process of how stars form in general. So there are originally 2 classes of these eruptive young stars. There are long-term outbursts called FU or ionist type objects. And by long-term, I mean decades, even up to a century. We don't exactly know because all the known FURs are still during their outburst. And there are short-term examples called EX loopy type objects or XORs. These objects have repeated outbursts once every few years, and they have timescales from half a year to a year. And these objects are not just different because of their light curves, but one way to distinguish between them is through spectroscopy, because FURs show predominantly absorption lines in their spectra, while XORs show emission lines. And of course, there's a lot more to eruptive young stars than just these 2 types. And to be able to know more about that, of course, we need to study, or we need to discover as many examples as possible. And actually that started like in the past decade. Their numbers started to increase a lot. I will talk about this more, but in 2014, we knew about 40 eruptive young stars, including candidates. And this year, there is just a catalog published today, actually, on AstroPH, which includes 174 examples of confirmed eruptive ISOs and even more 355 candidates by Contreras Peña et al. And this difference is due to surveys such as Gaia. So the way that we try to find some new candidates is through surveys such as the Gaia alerts. Even now, we have a lot more interesting targets now that Gaia is over. So once we find an interesting Gaia alert or some other alert like ZTF, we take spectroscopy to be able to confirm whether these targets are indeed eruptive young stars. So just to summarize what we have so far, but then I will go into more new results. We found more than 140 eruptive young star candidates just from the Gaia alerts and obtained quite a lot of spectra. I believe it's a lot more than 50 now. We discovered 3 XOR type eruptive young stars. and another 3 fjords, 3 more, which are like in between fjords and exors, and also investigated some other cases where the objects turned out to be non-eruptive, but still interesting. So I'm going to give you some new results, like what happened since the past Gaia Science Alerts meeting. As I mentioned, there is a new catalog, which is on AstroPH today by Contreras Peña et al. It shows the the eruptive VSO discoveries per year. And we can see that the discoveries have become more rapid thanks to surveys such as Gaia, VISE, ZTF, VVV. And this current version of the catalog includes 16 exors, 49 fjords, more fjord-like objects, which are like fjords, but we didn't observe the outburst, so we don't know when the outburst started, but based on spectroscopy, they are fjord-like. And there's a large class called peculiar or V1647 Ori-like targets or MNORs. This is not a very clear category, so these are objects which show mixed properties between exors and fjords, typically exor-like spectrum, but a longer time scale. And there are a few quasi-periodic light curves. I will show an example of that as well. And so actually this website of the catalog just became available today. Here's the link on my slide. It includes information on the targets such as VSO class, distance, the year of the outburst, if it's known, stellar parameters, mass and luminosity, visual extinction and accretion rate, and also the amplitude of the variability, and one can also download the light curves. So now I will just show 2 examples, which are very recent from our group. There is a target Gaia 20 DSK, which turned out to be an example of this peculiar category, MNOR, let's say. It has different names, which shows mixed properties of exors and fjords. So it shows 2 1.8 magnitude bursts. And the duration of this first burst, which is already finished, is about 2 years. We studied its VLTX shooter light curve, which shows emission lines. And from those emission lines, we could calculate the accretion rate, which confirms that indeed it's an eruptive VSO. And so we classified it as an MNOR, which is this intermediate category. And this is a work done by Patrick Nemeth, a PhD student in our group. There was this very interesting target, which in a long time scale, like a long light curve, it shows at least 7 brightening episodes. And these appear to be quasi-periodic. So the time scale of these outbursts is about 1.5 year, and the amplitude is about 2 magnitudes. So it looked like eruptive young star candidate with this crazy periodic behavior. Based on a periodogram analysis, we found the most dominant period to be 900 days. We have several spectra with VLTX shooter and IRTF, both during the bursts and in quiescence, so we could calculate the accretion rate. So however, the accretion rate in this case turned out to be closer to classical T-Taurus stars. So it cannot be classified as eruptive, but still I think it's a very interesting target. And this is a work currently in progress by a bachelor student in our group, Adam Matifi. And then our group started working on like larger samples of data. This is a nice example, a paper which will soon be submitted by Teresa Giannini. So this is a large survey, an LBT survey of 16 eruptive VSO candidates. And there were all kinds of targets, all kinds of young stars in this sample, mostly low mass, but there were some intermediate mass objects as well. And based on their light curves, there are like 2 main categories of them. There are those which have a stable baseline and clear peaks above them, so like well-defined outbursts. And there are those where there's a variability across the entire observation period. So based on the spectra, the accretion parameters can be derived. And you can see the accretion rates plotted versus the stellar masses. And one of the nicest or main results, I think, is that during the quiescence, so we have accretion rates during quiescence and outbursts as well. And during quiescence, we can see that these accretion parameters are close to the range of, or within the range of classical Tauri stars, which actually suggests that indeed all low and intermediate mass objects may experience episodic accretion. So this is my work in progress, and it's much earlier stage. It won't be submitted very, very soon, but hopefully it's still this year. I chose 12 targets from our IRTF survey, and we have all kinds of light curves, all kinds of objects, and I'm just showing here 4 examples. We have targets which show light curves that are XOR-like. One example of Gaia is Gaia 24CCY, which is actually an XOR. It's just not published yet. And then there are some light curves which do not look like typical eruptive VSO light curves, but the optical and mid-infrared variability is well correlated, like Gaia 22AAI. And then there are light curves with optical and infrared variability, but they are not really correlated, which is an example is Gaia 23 dBm. And there are light curves where we see a large amplitude optical variability, like this ZTF target, but in the mid-infrared, there's not a lot of variability. So also the spectra are quite different, but this is probably, I mean, it contributes that some of these spectra were observed during the outburst and some during quiescence. So this is what gives a challenge to comparing these objects. However, one way to compare them is that they all have emission lines from which we can calculate the accretion parameters, so we can analyze them with the same method. So what I'm currently working on is, well, we have validated their distances. We compared them to clusters and so on, like nearby stars, to be able to show that we have an accurate distance, because obviously if the distance is wrong, then the accretion parameters will be wrong as well. Then I take all the accretion tracers and convert them to accretion luminosities, like in the figure. For the right AV, they are extinction, they are supposed to be the same, like in this case. Well, not all the fits are this nice, but yeah. And then another analysis that I'm doing is excitation analysis. So comparing the Paschen series fluxes to models, and from this we get hydrogen temperature and density. So this is work very much in progress at the moment. So to summarize this, I've shown quite a few times here in this Gaia Alerts workshop that Gaia Alerts are also useful to identify some new eruptive young stars. And even if the Gaia mission is over, there's still a lot of work that can be done. And we also, so we continue to follow up the interesting Gaia alerts that we found, but we also started looking at ZTF alerts a lot. And we are looking forward to what can be done from the Vera Rubin Observatory survey. And recently, our main work includes works on larger samples, comparative studies of these eruptive young star candidates. And that's all. Thank you.
Questions?
There's one. So.
On Zoom. So we can start with a Zoom maybe first. Yes?
Hi, this is Josh Hamsch again. Thank you for your presentation. At Rhode Observatory, I'm also observing YSOs, especially for the HOIS project, hunting outbursting young stars. It's a project where Dirk Fröbrich from York University in the UK is the PI. He's also part of this paper which you mentioned of the catalog. I just saw that you have been observing Gaia 24 CCY. I'm also observing this star. I have about 1800 photometric observation in 4 filters at the AWSO. And yeah, I see variation of yeah, at least 2 magnitudes in different filters. And for the moment, the star is back to magnitude 18 in the blue filter and magnitude 13.5 in the I filter. Yeah, just to mention this. Thank you.
Yeah, thank you. It's good to know. I just want to mention that this target is part of my paper, but another group is preparing a paper on this target 24CCY. So probably a paper will be out very soon, confirming that it's an XOR. I don't know if you want to collaborate with them. I can arrange it.
Yes, of course. I mean, I'm interested. I'm a scientist as well. I'm a retired nuclear physicist and amateur astronomer. Maybe you know, I'm since a couple of years Gaia Alert follow-up, and I have a presentation at the end of the day on my work. Yes, of course. Yeah, please.
Okay, thank you, Josh. So, Sophia, do you want to comment on more to the comment of Josh?
Is there a comment?
No. I mean, to that comment. So yeah, so you will probably stay in touch, right?
Yes, of course. Yeah.
Okay. Thank you very much. Let's thank Sophia. We have to move forward. Thanks a lot. So the next talk will be given by Juan Cortina, and it will be about fast observations of nova ejecta with optical intensity interferometers. So, yeah.
Stay close.
Okay. Hello, everyone. So I'll introduce another use case, and you can help me with your alerts. So I'm from CIEMAT in Madrid and ISE here in Tenerife, and this work is with my colleagues from CIEMAT, Alejo Cifuentes and Tarejas. So what we are doing is this fast observations of nova ejecta with optical intensity interferometers. I guess you all know what a nova is. Just want to make you aware that that these ejecta expand and they expand very quickly. So to give you an idea, the expansion speed is from hundreds of kilometers per second to thousands of kilometers per second. So they expand very quickly. They can be observed in many wavelengths, up to very high energy gamma rays, actually. The expansion is very fast, and the ejecta have been actually measured to expand with interferometers. So interferometers is the only way to get an access to really the shape and the angular size of the expansion. We are talking about scales of milli-arc seconds. Okay. So what you see here was from a paper of the Chara instrument, where you see the angular diameter of the ejecta as a function of time. So in a matter of 1 month or so, it has expanded to 6 milliards or so, and you can measure how it expands, how the shell expands. You can take on, and you can actually see that sometimes the speed seems to change. So this was published in Nature already back in 2014, but there are very few measurements like this one. We also know from observations years after the actual eruption, years where the ejecta have expanded a lot. So here we are talking about arc seconds, okay, that the ejecta are not symmetric. Okay, so you see funny things like these bipolar eruptions here on the right, bottom right, or you see things like 70 years after the eruption of RR peak, you see things like a ring, okay? So this we know from observations years after the eruption, but we would like to know from the observation, we would like to see that in the observations after a few hours or days after the eruption, right? With interferometers. So what we are doing these days, this is a picture from these beautiful telescopes we have not on this island, but on the nearby island of La Palma, at the Roque de los Muchachos. We have these huge telescopes. On the left, you see these 17-meter Cherenkov telescopes for gamma ray observations. And we are building these new 23-meter telescopes, okay, LST, large-size telescopes of CTAO. Okay, so what we've been doing, well, this will be very much covered by the invited talk of Alicia tomorrow for gamma rays. But this can also be used for very high energy, very high angular resolution observations in the visible range. Okay, so these guys are for gamma rays typically, but we use them for visible observations, very high angular resolution. So what we do is we actually don't do amplitude interferometry like VLTI or CHERA. We do intensity interferometry. And what we do is we look at correlations in time of the light intensity that we measure in both telescopes. We are looking for correlation fluctuations in time scales of nanoseconds. Okay. When you find these correlations, depending on the degree of the correlation and how it changes with the baseline, with the distance between the telescopes, that's pretty much like a standard amplitude interferometry. We can measure the angular size of the telescopes, of the source. Typically in the angular range between 0.2 and 1.3 milliarc seconds. Okay, so that's the angular scale we are sensitive to. So with the MAGIC telescopes, we are expanding this. We already incorporated one of these AO telescopes, and we are incorporating the others in the next years. So this simulation, what you see here is the angular diameter as a function of time, and these are hours after the eruption. So this is what you expect to see with the 4 LSTs that are now under commissioning and the MAGIC telescopes. What you expect to see for TCAB, which you know will very soon be a very bright nova eruption, hopefully. I guess many people are interested in this, like Yaroslav. Well, we expect to see the expansion of the ejecta for the first hours, right? When it goes up to something like 1 milliarc or so. But of course, we don't know the velocity, so it may be slower, it may be faster, so it may be a matter of a few hours until it makes it to 1 millisecond. It may be a matter of up to maybe half a day or something like that. Okay, but what really matters is that we are limited by this maximum angular scale of our interferometer. Okay, so there's nothing we can do about it. It's about the baselines, the distances between the telescopes. In a matter of hours, it's gone. For weaker novas that maybe are probably farther away. Okay, so they expand in angular scales more slowly. Okay, so maybe it will take in the order of 10 hours or maybe 24 hours, depending on the speed, right? So for very low novas, which are farther away, it may take actually days, okay, or even a month to until it goes away of our angular scales. Okay, this is another simulation for a nova that is 5.5 magnitudes, 3 kilopascal. Okay. We are actually trying to improve our instrumentation. I told you we cannot change the distances between the telescopes. I mean, our typical distances are in the order of 100 meters, 50 meters or so. But there's a trick we can play. We can actually look for correlations between parts of the mirrors. And these telescopes are so big that even part of the mirror can be like 10 meters away from the other one, right? So the baselines we would be talking about are in the order of 10 meters or something like that. And like this, we could actually follow novas for even longer, okay, up to many days for very bright novas. Okay, this is actually submitted for publication. But where we are now, and here I want to come to you and tell you what we need with our current instrumentation is for a nearby nova like TCAB, as I told you, the shell grows so fast that it becomes undetectable for our interferometer after a few hours, maximum 1 day, 2 days. Okay. And then also brightness goes down very fast. So it's not very good for us. We are sensitive to mainly bright novas. Okay, so timing is essential. We need to get alerts very quickly, if possible in the order 1 hour or even less. But it's bright novas, so I mean, anybody could detect these novas, right? Less the magnitude or so. So any small telescope. So I think we need some network or some way to get the alerts to us right now. And this may be a handicap of the chunk of astronomers, but we depend on all these ATELs and GCNs and all that. Maybe we are just misinformed, but we are not getting all the alerts that I think we should be getting. So we would desperately need some kind of more reliable alert system. Okay, that was it. Thank you.
Thank you very much. Do you have any questions? David?
David Buckley, South African Astronomical Observatory. Do you know if similar attempts are being considered with the HESS TV gamma ray array at all?
Mm-hmm. So yeah, in the last years, all types of telescopes are getting equipped like this. So this started with Veritas, the Americans, and then we follow up, and it has recently also introduced instrumentation. So, and as you can see, the plan is for the whole CTA, the 2 sites in the north and in the south, to be fully equipped like this. Yeah.
Any more? Yeah.
Priscilla Pesci from Stockholm University. Thank you for the very interesting talk. Just a comment. So on the alerts, if you are looking for optical alerts, I would say maybe you can look into the brokers. There are different, like the LSST official brokers, alerts, I think, and so on. They ingest data even before it is reported into ATELs or GCNs or anything. And many of them have like light core classifiers or alert classifier, even stamp classifiers. So you could filter on things that are possibly novice or something. I don't know if you have looked into that. It's just
Okay, thank you. Well, LST is not terribly good for us because we are in the north. But you mean that there's a general tool?
Yeah, so the brokers are for LSST, but right now they ingest CTF data. So it's actually all the alerts from the north.
Okay.
One more? Yeah, in the back.
Yeah, Nadia Blagorodnova from University of Barcelona. So yeah, my comment is that all these brokers and like TNS, for example, is very focused on like extragalactic science, right? So we love that. So like most surveys, like, I mean, not Gaia is reporting everything, but like many people also despise Gaia because they also reported like not extragalactic transient. So yeah, I just want to like indeed say that I don't see there is a niche, let's say, yet. Maybe astrocolibri could be, but like for reporting these more like brighter galactic transients, like novae or like young stellar objects or other things. I mean, we would love to have like a place for this as well, because I mean, LSST is all extragalactic, brokers are mostly extragalactic, but yeah, like I want to raise the awareness that I don't see right now like the place to go. You know, there's like some options, but as a community, I think we should agree on like something that we say, okay, this is the spot.
Very good point. Fabian Schüssler, you're free. I totally agree. One source of novae that we use in astrocolibri is the Central Bureau of Astronomical Telegrams. That's a thing that exists since 150 years, and where a lot of also amateur astronomers report possible novae sightings, and we pass that and make it available as a push notification on your smartphone, so you don't have to read that horrible website that they put up. So that's one source of information, but if there are others, I'm happy to hear about that. Yeah.
For many wavelengths, timing is not so important. I mean, I'm doing these observations with in gamma rays with the same telescopes, right? With the same Cherenkov telescopes, but they can wait a couple of days, or they would love those as soon as possible. But it's not so terrible if they are 1 day late. But if we are a few hours late, we are done. I mean, the ejector is so big we cannot see.
Łukasz Rzekowski, Warsaw University. Just a quick comment. So, first of all, I agree that there is no central spot, but TNS with Gaia, actually, we kind of forced them by hand to include novae. I see novae candidates in TNS. But one more comment is that these novae, they don't, the bright ones, they take time to rise, right? So that's probably the period we should focus on to get ready for these. Maybe we have hours, maybe a day or so, right? Before they get very bright. So we should look for transients which are fairly faint, which could be reported in TNS, then aim with the follow-up to see what they are doing. And once they reach the magnitude limit you are interested in, then we send you an alert. I think this is the way I would see it.
Yeah, I was suspecting this comment. I don't know. Some of them are faster than others, right? I mean, you know, so I want to prepare myself for the worst case scenario, right? Fast one.
Sorry, Priscilla again. Just a last comment related to this. So one thing is CTF that produces alerts. Of course, it's not as Gaia, but CTF produces alerts and the brokers ingest all the alerts. Not all the alerts go to TNS or to ATEL or something like that. So if you, so there are things that are reported, but if you look directly into the broker, you will see fainter things that can be classified also with the internal classifiers that they have that are not reported anywhere other than in the broker. So you can make your own filter to see alerts that you are interested in real time. That maybe this will never get to TNS or an ATEL or nothing like that.
Okay, thank you. So let's thank the speaker and let's thank all the, okay, but yeah, we can actually continue then during the lunch break. And we have a last talk of the session that's gonna be given remotely by Karolina Bąkowska from Nicolaus Copernicus University in Toruń. Hello, Karolina, we can see you.
Hi, I hear you well. Do you hear me?
Yes, we can hear you well. Good to see you. And let's just move to your presentation.
Okay, let me know if you see it.
You can see beautiful trees. I guess it's just next to your home.
No, I was sharing the presentation, so it's not this. Okay, do you see it now, maybe?
We can see you working in a garden, I guess, so...
No presentation still.
No. I mean, so we steal the presentation with a very nice image and graphics. Yes, it works well. Karolina Bąkowska, BH-Tom, a shovel for digging cataclysmic variables. So the stage is yours, Karolina.
Okay, thank you very much. I'm sorry, 2 minutes ago I had a power blackout at my home, so it's a little bit stressful for me right now because I don't know what is going on with electricity right now at my home. I will be quick because I know that I have the very special prime time just before lunch, so I will just want to make some short summary for the work my whole team did within the recent few years. And actually, I want to say really huge thanks to Łukasz and all the team who is developing this amazing tool, which is a black hole tom. Because right now, when we have like such a overflow of data, any data in cataclysmic variables also, looking for them, looking for some features of them is like looking for the needle in a haystack. So that's why this title and this image. And last few years, I was, of course, delegating, searching for some phenomena and for some properties of stars to my students. That's why I can nicely summarize the results we obtain, not in the results. I will present you all the tables and figures and so on. It wouldn't be enough time for it, but I decided to say special thanks for them also, especially that most of them are present right now with you on the beautiful Tenerife island. And look how it ended the last 4 years, that we already have 4 bachelor degrees titles based on the data found on the black hole TOM tool, and 2 master degree theses. And these 2 theses, they finished not only with the defense, but Bartek is doing some last corrections of the paper we will submit this month, and Mateusz will definitely submit the paper regarding the stars he was focused on till the end of this year. So we also have not only results in degrees for the students, which is for them most important, but very important scientific results. And if you want to know more, Łukasz is always recording everything. So the talk and studies dedicated to a very active dwarf nova, Ursa Majoris, which Bartek was studying, is from 2 years ago, I think. It was presented on the Gaia Alert workshop. Mateusz also was present and showed some results regarding PAX Andromeda and SW Sextansi stars last year. Barbara was presenting study of polar last year also. And today Tymek will have a short poster talk regarding EX Draconis. So you will see this result also. And this is what has been already done, but it's not the end of the story. Of course, you can see my beautiful students here who defended beautifully. So it was like a really nice time for all of us. But the story continues. Not only I am very persistent and focused on cataclysmic variables, but my students, they don't discourage easily. And Barbara will continue her research on these objects during her master thesis. Piotr is studying very known objects. Many of you participated in observations, but based on the talk you saw, they presented today, they spent some time recently on the development of our observational log. So he probably will show some final conclusions about these ETF objects next year to you. And I just found out that I have 2 new PhD students, Bartek and Mateusz, will also continue their research regarding cataclysmic variables. So definitely we'll be using black hole tool for their studies in future months and years. And I will tell you some more things about ACMEs, which Barbara will be investigating as soon as she will come to Torun. Because I have a call for observations to all of you. If you have any tool, doesn't matter how big telescopes you have and so how much time do you have and on which hemisphere. We already have a very nice list of objects for which we would like you to ask if it is possible for you to join our campaign. So ACME objects, what they are like, because we can label them as a subgroup of cataclysmic variables, but we can call them as a little bit more distant cousins. It depends who you ask. The difference is that these compact binaries are not built with the white dwarf as primary and like main sequence star as a secondary, but in this group of objects we have 2 white dwarfs. And of course the orbital periods are way shorter, below 70 minutes. The shortest known objects is like with 5 minutes of orbital period. The matter is of course accreted by the more denser and compact objects. In some cases the accretion disk is also formed, and we see the same or similar behavior to the cataclysmic variables with frequent outburst activity and intense increase of brightness. And for many years, we known only a few objects of them. The first one was discovered by Polish astronomer Joe Smak in 1960s. But then until 2015, actually, we know like only a handful of them, like 20 or less. And a very important paper was published by the group led by Levitin. He focused on 11 of these objects with outburst activity, and he monitored the activity and tried to find some independence between the orbital period value, which you can find on this figure on the x-axis, and some outburst recurrence time, so how many days it is between one outburst and the second one, the outburst magnitude or amplitude, or the duration of the outburst. And he found some plus minus, we can say, approximately linear increases and see some dependencies, the longer orbital period, the longer recurrence time. But right now we have some doubts about this dependence, and they also don't fit nicely to the models we try to build for ACMEs, because their behavior is way more mysterious for us than cataclysmic variables. And right now we can see what a plethora of data we have right now, because it only was a decade, and right now we know over 120 stars of this kind of objects. And we can even divide them based on their activity, whether they are mainly in a high state activity or low state or outbursting. Nevertheless, we can choose among them many objects and monitor the outburst activity. And if we start with, for example, Atlas catalog, we can see in many cases, like on the first plot or in the middle, that we can see some increases in brightness, but we cannot be sure whether we didn't omit some outburst and what's going on, why it is, like, for example, so messy. In some cases, like this right figure, you can see very nice outbursts. So in this case, it is easier to monitor, but the standard monitoring provided like by Atlas or Assassin, which can be easily checked by BHTOM, is not enough for us. So what I would like you to ask is, if you have a time, doesn't matter how many nights per year, you can make a 1-2 exposures for any of our objects. So me and Barbara, we will prepare a list and we will send it to the newsletter. And please add it regularly to BHTOM. We will be checking and we will be monitoring, and based on this, we can then create a good sample of the outburst behavior of these systems and then publish the results. Most of them have the brightness rather dim, around 18 or 20 in the minimum brightness, and they are of course brighter during the outburst. And if you cannot catch them in the minimum phase, don't worry, it's okay. For us, it is the most important part to mainly know when they are bright. So if you cannot see them, but you can monitor them and detect them in the maximum brightness, and then at the point, we just need one person with bigger telescope to have a point before or after outburst to know that there was the activity detected by these systems. So it is not that way that you have to choose only the brightest. You can just see that there is no detection. Of course, it would be difficult to upload them to BHTOM, but you can also write directly to me or to Barbara and let us know that, for example, you monitor it for the last week or month and it is still no detection of signal, which means it is the low state of the brightness. So I would like to also thank to people who are already monitoring first of these objects I add to the black hole TOM catalog. Assassin 14cc, it is an object from the southern hemisphere. As you can see, we have not only the catalog data, but already from people who are adding observations from the southern hemisphere. It's really valuable because based on this, I already can detect and calculate some statistics of the outburst activity. So we already really monitor this and see whether you are adding some data. So really, thank you very much for that. That is all for me. Thank you very much. If you have any questions, comments, you can ask this right now or go to lunch, write to me, or ask my students that are there. Thank you very much.
Thank you, Carolina. Do we have any questions or comments regarding the work that was shown? So it's impressive. Oh, I see there is a question from Josh, right? Please.
Yes, again, me.
Yes.
So, I mean, I would propose to check the AVSO database for AMCVs because you may know that there is an organization which is called CBA, Center for Backyard Astrophysics, who is following these targets, and I'm part of CBA, and I do the Southern Hemisphere targets. For instance, I saw in your list of one of these publications, V803 Centaurus. This is, I mean, one of my targets, which I have thousands of images and observations, and they are not in BH-TOM yet, because I mean, I start to supply BH-TOM with targets of interest to BH-TOM, but I have maybe 100,000 images of CVs which are not yet in BH-TOM because they cannot follow. They are still 100 gigabyte of data waiting for download into BH-TOM from my side.
Definitely me and Barbara will contact you with this, and I'm fully aware of AVSO. We usually frequently use this, the same as Atlas, Assassin, and so on. Black hole TOM is actually, frankly speaking, right now way more convenient because most of the data are already there, so I don't have to send API request to Atlas, for example, and make it separately. I can check easily here, so I definitely prefer by myself to check it in one place. But of course, I know that it is tedious work to upload all the data you have to this tool, because we struggle in Piwnice with the same. That's why Barbara and Piotrek are working so hard to make any nice pipeline for awareness with the data in Piwnice. So
yeah, actually,
I know it's work in progress.
AVSO can also be accessed rather easily and downloaded. I mean, you just mentioned 14cc, Assassin 14cc. I have data from Assassin 14cc, 3,000 images or points submitted to the AVSO in the years 2014. 2014, yeah.
That would be great. Thank you. So we definitely will contact you, Josh.
Thank you.
Thank you very much. Thank you, Carolina, for the talk. Great response to your team, led by you. Thank you, Josh, for the questions. And we are moving towards the lunch. Lunch breaks. Thanks all of the speakers of this session before, like, morning session. I don't see any additional announcements. Just a reminder that 1:10, right? The tour to the ISP starts. So enjoy your lunch. And Paul also wants to add something. Yes.
Yeah, and just to say, thank you everyone who filled out the form for the buses. We have 11 people going up to Teide by car. Yeah, so we all have a seat on the bus who needs it. Thank you for driving. And yeah, the drivers perhaps should contact me today or tomorrow, that we can coordinate how to get into the observatory. Otherwise, enjoy your lunch.
Thank you. Anna, could we put on the slide, Anna? Okay. I have my name, but didn't hear you. I was wondering if, because I don't know, Łukasz is not here, so I wanted to put the slide with the last slide of Miłosz and Jakub talk.
Ah, yes.
Do you have this power or?
I can share it myself, yeah.
Ah, super. Thank you. So there will be these contact details to Miłosz and Jakub. So the slide that was missing at the talk. So you can see it. And we will also start the session with that. So yeah. Yes. Yeah, we can leave it at. Tak, możemy zostawić.
No i tak to wygląda. No strasznie.
I didn't move. I just uploaded it and didn't move it, and that I can see it in the Dropbox.
Okay, so if you see that in
Yeah.
our Dropbox,
Yeah.
that's our computer, no? It's
Yeah.
or it's yours.
That's yours. I just uploaded into the Dropbox, so it's not in the.
Yeah, that Anna will do that from behind. So it's in the
In the file request. Okay, perfect. Okay. Thank you.
Was nicht gar nicht. Und ja, dann ist es ja, ja. Das ist ein Lebensschau, 70 Jahre auf normal. Ja, 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 das ist der blaue Filter. Das schaut aber bis so die Auflösung nicht so schnell. Weißt du. Yeah, I prepared it and I wasn't aware that it would be digital form.
Yeah.
So I decided to be printed out with the quality. But
Yeah.
yeah, I have it. So I came here already last week, so I have had time. So if you have any questions, no, I have no questions. Yeah, so if you have any questions for you, if you want to look at it better, so like part and there's our website and on the bottom there's also a link to the folder or at least the PDF folder. And there is yeah, and there is some better link and folder on the slide. Yeah. So you can also, for example, that case, for the home, I had to write write a drive number, and that's really
How did
Yeah. Yes, we have one. Yes, Maria, I can tell one. No, I was. We don't know.
Forgot to share the screen. Use this or just this? The button. It works.
Thank you all. Welcome back. We're going to have a series of talks on, I want to call them dippers, but maybe this is not exactly what's going on, especially if they're not young stars. So here's the main sequence star with dimming events. So I'd like to invite Nadia to tell us all about Assassin 24FW. Take it away.
Thank you. Hi, everybody. So most of you don't know me. I've spent a lot of my time in extragalactic astrophysics, and now all of a sudden I'm finding myself a co-author with half of this room. So that's a very interesting situation to be in. So I'm going to tell you about this interesting event, Assassin 24FW. I'll start by telling you about the event itself, then about the spectroscopy that we obtained during the event. Then I will do a little bit of wild hand waving and hypothesizing. And then I will show a couple of cases of other dimming events, which may or may not have some similarities to Assassin 24FW. So I should also say that Raquel, who is here and who is giving the talk right after mine, will also speak about the same event, possibly with some differences and similarities in interpretation and then the data that she's presenting. So we led two completely simultaneous, completely independent papers on the source posted within 24 hours of each other. I'm too old for this drama, I think. So I don't know how well I can handle transient astronomy, so we'll see. Okay, so the event, oops, I skipped. So in the top right corner, you will see that this was a 13th magnitude star doing absolutely nothing interesting in particular for 10 years. And all of a sudden it went into this 4 magnitude occultation, dimming, eclipse, whatever you want to call it, and stayed in there for 8.5 months. Assassin triggered on it in the end of September 2024. It is by the color magnitude diagram, appears to be a main sequence star, as illustrated here. Very quickly after the Assassin triggered, Nair and Denisenko published historic results from historic photometry from DASH. This is a re-rendition of the same from Yaroslav. And you can see that there were 2 more events, one in 1937 and one in 1981, where the star disappeared from the historic plates. So the 3 panels show before, during, and after the hypothetical eclipses in 1937 and 1981. These are the light curves that we obtained. So in the middle panel, those are the publicly available data from Atlas and AAVSO. But in the bottom panel, this is the BH-TOM. All of you contributed to this. So you have seen this. The main conclusions from this BH-TOM light curve is it's very smooth with an 0.1 magnitudes, quite symmetric also with an 0.1 magnitudes. And it shows a lot of dimming, but not a lot of reddening. Raquel actually has a very nice dust model that explains this in quantitative detail with additional data that I hope she will talk about. But the bottom line is what this means when the star dims but does not become red during the dimming is very likely small grains are missing, because in an extreme case when it's being blocked by big rocks, then it just dims and does not redden. So it's an interesting physical situation already. You can see that we obtained 5 epochs of follow-up spectroscopy. So those are marked with the vertical blue lines. And I'm going to be presenting results from this last epoch, which is marked Gemini, because this is the highest resolution spectrum that I got using director's discretionary time on Gemini. So all 5 epochs of spectroscopy show deep sodium absorption, and in the Gemini spectrum, we can spectrally resolve it in excruciating detail. It's not consistent. There is a little bit of sodium absorption in stellar photospheres. So after subtracting that, you get the stop line. So you can see that there's very deep sodium absorption, which is also not consistent to all appearances with the interstellar medium. And here I'm showing you zoom in on one of the sodium lines and all the different kinematic components. And the solid orange line shows the Gaia radial velocity of the photosphere of the star, 36 kilometers per second in the heliocentric frame. Whereas you can see that the sodium absorption is blue shifted relative to that by 27 kilometers per second. Okay, interesting. So all the spectra show that. I'm just showing the Gemini spectrum because it has the highest resolution. We also see broad and blue shifted H alpha. So if you look at the second from the bottom curve, the dark blue curve is the data. The light blue curve is the stellar photosphere. So we subtract the stellar photosphere to reveal the excess emission. And so the bottom spectrum shows just H alpha emission now corrected for the stellar photosphere. And the top 2 curves show H beta and H gamma, where there's basically nothing. But interestingly, in the passion lines, there's something. So fashion lines are in the near infrared. The quality of the spectra wasn't as good, but you can see that there is some blue shifted excess over the stellar photosphere, which is again shown in the light blue line. These profiles, broad blue shifted, are similar to those seen in young stellar objects. In our case, it may be time varying. Okay, but this is the most tantalizing discovery in the Gemini spectrum. So I see dozens of narrow metal lines. So this is again illustrated in this right panel. This is just a subset. There's more. So again, the vertical solid dashed line is where the stellar photosphere is. So there's a bunch of absorption lines in the stellar photosphere all lined up with the vertical orange line. And then you can see that at the dashed line location, there are these spikes that are the metal emission lines corresponding to these photospheric absorption lines from all these weird elements, strontium, calcium, chromium, iron, whatever. Again, it's the same offset as in the sodium D, so minus 27 kilometers per second. This is very different from anything seen in young stellar objects, as far as I know. Okay, so now we have a situation. We have a star whose photospheric fits, lack of lithium, modest rotational broadening, and high velocity relative to galactic rotation all suggest that the object is old. So 2 gigayears plus is the best fit from pre-occultation photometry. But at the same time, the star has infrared excess before the occultation, as seen in the spectral energy distribution, and broad H-alpha emission. So those are typically considered to be signs of youth. So there's the discrepancy here. Okay, so now we're thinking about it. So consuming raw or undercooked data may increase risk of confusion. So I'm going to hand wave a lot. But here's what I'm thinking right now. So I think that the star is old, and I think that it got populated with gas and dust during a relatively recent planet-planet collision. So it suffered some kind of dynamical instability. Planets collided, produced a cloud of debris. So there is now a product secondary that retains a cloud of debris. So it's moving around on this 44-year orbit that's seen in the historical data. One possibility of estimating the mass of that secondary is that if it's tidally limited, so if it's limited in size by tidal forces, then the time of the transit can be recast as mass. It gives a minimal mass of the object required to gravitationally bind this disk of a few Jupiter masses. Okay, and then so this is this gray cloud that you're looking at here, and then rocks and dust collide and grind down and produce gaseous winds of these high, of these metals that we see in the Gemini spectrum. And so that's meant to be illustrated with these blue arrows for the wind. Okay, so there are alternative models, and Raquel will tell you all about them. How unique versus not unique is the source? So events around main sequence stars are actually quite rare. So here is a little assembly of some interesting events with some similarities. So I have found a few events that are hypothesized to be gas poor. And the distinction is that all of those events show sharp substructures in the light curves. You probably are all familiar with this Boyajian star, which is hypothesized to be a cloud of comets or a disrupted planet. You may have seen this Mamayak object, which is a candidate thin disk with rings around the planet. So the idea is that these narrow dips are produced as the Saturn-like thing is transiting in front of the star. The top object is a main sequence star. The bottom object is a young star, but no infrared excess. Here is an intermediate age star, 150 megayears, again, best fit by this ring, thin, gas poor, slightly inclined, slightly offset from the perfect impact parameter disk ring. Okay, so the difference is that if you have thin disks that don't have a lot of gas, they very commonly produce these sharp features and asymmetric shapes like this one, whereas Assassin 24FW has this very smooth light curve, very symmetric. Again, there's an 0.1 magnitude asymmetry, which could be interesting. But we also see, of course, all kinds of signs that it's likely gas rich. And then the metal emission lines that we see in Assassin 24FW are unprecedented. Here's another relevant type of variability. So we see, I found 2 or 3 sources where the optical dips are seen roughly at the same time as the infrared emission increases. And so the idea here is that, again, there's some sort of a violent thing going on. Let's say that it's a collision of planets or planetesimals, and they produce a lot of dust. This dust gets produced, gets heated up, infrared rises up, and then this cloud of debris comes in front of the star and produces these dips that you see in the top panel. Okay, so I have not been able to find a really bona fide main sequence star in this category. I have this one candidate at 300 megayears, and then another that I'm not showing at 10, and maybe another at 15. So this is more common in relatively young stars, which it makes sense because they are still working out their dynamical situation. So Assassin 24FW would be old for this process, but not impossible. There's some recent work, theoretical work, that suggests that even a 2 gigayear star could do this. And so, of course, in Assassin 24FW, the event would have been well before 1937, and so the debris no longer manifests in the same way. All right, so conclusions. So this is a really interesting event. Very long, very smooth occultation, a period, maybe orbital period, maybe some other period of 44 years. Photospheric indicators and galactic kinematics suggest the star is old, but it has circumstellar dust and H-alpha emission. And these metal emission and sodium absorption lines are unprecedented, suggest debris grinding down and producing perhaps a wind of gaseous metals. And perhaps this is a result of a planet-planet collision that we are observing a little further down the line than these other examples. Okay, that's all I have.
Thank you very much. Do we have questions? We have a couple of minutes. Laurent.
So I'm not, maybe I missed something. So because obviously, as the comment of Simon at the beginning of your talk, there are for young stellar objects dippers. And so are there the classical YSO dippers have sometimes smooth variation?
So, okay. I went into this thinking this was a young star, and I really twisted myself into a pretzel trying to, think of it as a young stellar object. And then we just kept having more and more evidence that this was a 2 gigayear star. So we started with the photospheric fits. They were converging to a 2.4 gigayear solution, but then there's just no lithium in the photosphere at all. And we have a very stringent upper limit on the lithium. So to the best of my knowledge, this is not a young star. Okay, and the phenomenology with young stellar objects is different. So the dippers have irregular, aperiodic, light curve with typical variability of a few days, suggesting some sort of sublimation distance limited kind of situation. This is much further out. This is 14 AU. This object, Boyajian star, these guys have some estimates. They also suggest a few to 10 AU. This is a main sequence star. So this is also dipping like variability, debris. So why this one is clumpy and Assassin 24FW is so smooth, that's a great mystery. There's no sign of gas in the Boyajian star, so that's interesting. Something is different.
Łukasz?
Okay, that's great. It's for us from the Beeston point of view, this is an amazing, yet another beautiful use case of the network. But I wanted to ask from our telescope perspective. So, could you comment on the data we provided? Was it, you know, the frequency or the wavelengths, the filters? Was it optimal? Would you have done it this differently? And there's another follow-up question: what can we do now if the event after the event is over?
So I was just talking to, okay. There's one more thing I want to do with BHTOM data, if it's possible. There is a 3 arcsecond object, which away from the main source. And it was not visible when the star was in the bright state. Because I think it's about 19th magnitude. So it would have been 6 magnitude difference over 3 arcseconds, not good. Gaia gives something for it. It knows that there's a source there, but the photometry is off. In the dim state, we saw it in our acquisition images and kind of made sure that we didn't acquire the wrong source. And then I said to myself, what if it's a companion at 3000 AU? Okay, so now what I really want with BHTOM, and you guys can tell me if it's possible or not, to take the frames that have good seeing and to stack them as much as possible by filter and give me the colors of the companion to see if I can get the photometric parallax for it, and if I can see if it's consistent with being at the same distance as the target star. And it can only be done with the historical data because it's already in the bright state and we cannot do it anymore.
Thanks very much. I think we have to move on. Raquel is our next speaker. Thank you.
So you can either press here or into the matching thing.
Okay. Hello, everyone. I'm Raquel Forester-Ibio, and I'm a postdoc at the Ohio State University, and I will keep talking about Assassin 24FW and the role that time domain surveys play in finding these long and deep stellar dimmings. So first of all, I will introduce the Assassin survey itself. Assassin stands for All Sky Automatic Survey for Supernova, and it consists of 20 robotic telescopes located in Hawaii, Texas, Chile, and South Africa of 14 centimeters in diameter. They survey the entire night sky since 2012, and we have collected so far about 14 million images. As the name states, Assassin stands for tries to discover supernova explosions, but there is a lot of more science that can be done with this survey. And here I name a few examples that can be done apart from finding supernova explosions. So if you're interested, all data is publicly available through these 2 websites and also through BHTOM. And just by typing here the coordinates in the portal, you can get the photometry of your object and download the light curve data. And now moving to Assassin 24FW itself, it was discovered as part of Assassin normal operations and reported in the Astronomer's Telegram on September 27 last year. And here I will show the most important key points of this work that we follow up this star. But here in the QR code, you can get the full paper on this object. So as we detected that the star was getting dimmer, we launched a photometric campaign in different filters to get the full eclipse. And as Nadia said, the eclipse lasted for about 8 months, and it's at most 4 magnitudes deep, which means that the star lost about 97% of its flux. We also have an optical spectrum at the beginning of the eclipse, 2 near-infrared spectra, and 5 polarization measurements through the whole eclipse. And during the dimmest phase, we detected that the light was polarized by 4%. Apart from the data that we have, there is some archival data. And soon after the actual discovery, another group published an Astronomer's Telegram suggesting that these upper limits in the Dazzler light curve are previous events of this system. And this highlights the importance of long baseline time domain surveys, because thanks to the DAS data, that started since the end of the 19th century, we can recover such long periods of this type of eclipses. Okay, and then moving on through to the SCD of the star. In the bright phase, we constrain that the star is an F-type star with some warm dust around it that we model it as a circumstellar dust. And the first thing that we notice in the dim phase is that the optical emission shape didn't change much. So we just rescaled down the emission of the star by 2.8%. Also, it's logic to think that this extended infrared emission of the dust is going to be present on the eclipse. And we have a second component to explain the eclipse in the SCD in the eclipse by this emission of the infrared. But with just these two components, we cannot explain the near-infrared fluxes in the middle. But thankfully, in our data, we have two hints that may help us understand these near-infrared fluxes. The first thing is that the optical emission shape didn't change much. So stars below this dashed line can emit in longer wavelengths without altering the optical spectra. And also in the near-infrared spectra, we realize that the bracket gamma is not present, but the other bracket series, we can detect them. So that means that there is something diluting the bracket gamma, but not diluting the others. And that's that gray band over there. So with these two pieces of information, we suggest that there is an M-star companion in the system, and that will fill the near-infrared fluxes in the dim phase. Okay, apart from that, we can learn more things about the culture by imposing that these smaller color changes, that's the gray band over there, and also that the light is polarized by 4%. We tried different compounds for different particle sizes, and we inferred that waterized carbon or graphite of 20 microns in size can produce enough polarization without altering too much the color of the eclipse. And that also gives us a hint on the origin of this occulter, because there has been evidence of large grains in protoplanetary disks, in extended rings around stars and exoplanets, and also from all collisions between planets. When the debris disk forms in a steady state, the smallest particles can be kicked out of the system due to the radiation pressure of the star. Now, since we have a tighter constraint on the age, maybe the protoplanetary disk hypothesis, it can be disfavored, but we are still working with these two other, the extended rings or some other old collision of a debris disk. Okay, we also wanted to propose a geometry with the elements that we know that they exist in the system. The first thing is the F-type star, that is the one that is getting the occultation. We have evidence for a smaller companion, and there must be some optically thick structure producing the occultation. So we realized if we put these two stars in a binary configuration, and there is an optically thick disk, and these binary interactions can induce precession on the disk. And given the masses of the stars and the separation between them, we can make precess the disk with the required 44-year period. But it is likely that this is not the last or the definite model, because now we have high resolution spectra on the dim phase, and we will acquire more data in the bright phase, and that will help us constrain the actual geometry on the system. And also mark this year on your calendars, because the next eclipse, it's going to happen, it's predicted to happen in 2068. Okay, apart from that, we wanted to know more properties about long and deep eclipses, and we searched in the literature for other systems with durations longer than a day and with flux decreases of about more than 20%. And we collected these 47 systems, and in this huge table, there are 2 Gaia alerts too. So we tried to systematically classify them, and there are 2 typical archetypes for these long and deep eclipses, but we realized that they are not enough to encompass the whole broad configurations that all these systems have. So we extended the categories. We extended the epsilon category to whatever systems that have an extended companion orbiting around the star. And we extended KH15D to systems that have large structure around them, not necessarily being a circumstellar or circumbinary disk itself. And then we plot the depth against the duration to see if we can extract some trends. And we can see that in the depth versus duration, there is no clear trends. But when we plotted the period with respect to the duration, we can see that Here we can see a split between the two categories. So for the same duration, systems like Epsilon or Gaia tend to have longer periods than systems with circumstellar disk or large structures around them. And this is kind of logical because if you have a large structure around you, you can spend more time of your period in the dim phase as compared if you have something orbiting around you that every now and then will pass in front of you. We also plot these systems in a color magnitude diagram to see if there is any preferential stellar type for this type of eclipses, but we found that they are all scattered in the CMD. We have main sequence stars, we have young stars, old stars, even white dwarfs. But when we plot the color diagram, we see that around half of them present mid-infrared excesses, which means that warm gas is present in these systems. And for the systems that don't have a mid-infrared excess, we suspect that in the far infrared, they are likely to have some excess because that seems essential to produce this type of events. Okay, so most part of these 47 systems were discovered serendipitously in different time domain surveys, and it is now when we are starting to search systematically for them. So in this work, we searched systematically in Assassin to find big stellar dippers and found these ones over here, where the first one is Assassin 24FW. And then another group searched for main sequence dippers in CTF and found 81 new systems. So this is exciting because as we get more and more examples of this type of population, we will be able to systematically classify them and try to find common features of all these systems that will help extract conclusions about the origin and the dynamical conditions that can lead to such eclipses. So to summarize, I want to highlight that Assassin 24FW is a remarkable long and deep eclipse, but not only that, its eclipse was achromatic and polarized, which help us constrain more properties about the culture itself. And when we look for long and deep eclipses, we found a very broad population, but around half of them present mid-infrared excesses. And hopefully with future systematic searches, we will help understand this rare population of eclipses. That will be all. Thank you.
Thank you very much. I'm going to ask a quick question before anyone else jumps in. You both speakers have commented on the smoothness of the eclipse, but I see quite a lot of structure in the bottom, and I wonder if any of this is real or it's really calibration problems in the photometry.
I mean, there are some wiggles over there. And
some wiggles, yeah.
Yeah, those wiggles align with full moon measurements.
Ah, okay. So
but there is also, maybe there is some substructure also hidden there, but it's smooth compared to other dippers. There are dippers that the light curves are completely a mess. And this one in particular is pretty symmetrical, given the circumstances of dippers in general.
And a follow-up question would be, do you have any spectra either before or after the ingress? I'm guessing the answer is no. We saw the beautiful spectra during the event, but...
We have, previous to the event, we don't have anything, and the star wasn't observable until now, and now is when we are going to get high-resolution spectra to get some, to track what is going on.
And track the gas emission question.
Yes, exactly.
Yes, thank you. Other questions?
Hi, this is Josh.
Go ahead, Josh.
Yeah, I have observed Assassin 24FV after the astronomer telegram was submitted, and I have sent the data to the AVSO. So I propose you also to check for dippers, the AVSO database, because I see in this picture that the AVSO is not mentioned. I mean, AVSO is a huge database with lots of valuable observations, and I have observed it, and I'm still observing it also after the dip in the bright state now in 3 or 4 filters. So compared to Assassin, there is at least some additional benefit in observations from other observatories.
Yeah, I think we look for OSU, but since we have all these photometric campaigns all of LSCGT, POISE, and ROSE involved, we just plug in our work the data that the people were involved in that. But yeah, I think Nadia has the measurements of so too. But
Yes.
yeah, obviously everything that we can observe and get more information will be valuable, for sure.
Yes, and if you have a list of interesting targets, you can submit it to me, and I will put them into my program and observe it.
Okay.
Because in 2068, I won't be available anymore.
Thank you very much, Josh. Laurent, you had a question.
Yes, I was curious if at the bright state, you see that the star is variable. For example, it could be Gamma Doradus stars, maybe with pulsation or any other variability. There was a study there?
Yeah, we look for test data, and there is a test sector previous to the event. Another one during the event, but it's so dim that test cannot get it. And previous to the event, we ran some periodicity values and everything, and we cannot see any periodicity of the star itself. So it was pretty full.
And are you waving your hand because you have a question?
Please, I have.
Go ahead, Jaroslav.
I'm just using my time now from a talk. I have a question about these big stellar deepers. So does this include also our Corona Borealis stars?
No, I don't think. I mean, I don't remember that in the sample there were any of those. We were just thinking about dimmers that happen every now and then that were long and deep itself.
But those could be long, no, and
okay.
could be deep.
Okay.
So I'm just wondering because there is
can look up.
not
Obviously,
many of them known. So
I mean, obviously, this table is not complete at all, and we will probably build upon this. And yeah, we can look into those too.
All right.
Yeah. Thank you.
Just to comment that the event happened, you'll need the Gaia DR5 data to get the beautifully calibrated light curve during the event, and then you'll get some spectroscopy
That will be great. Yeah.
during the event as well, but you have a little bit more of a wait.
Yeah, we have to wait.
So our next speaker cannot connect, so we're going to bring Yaroslav up now. Unless there are any more questions, we have a bit more time. No, then we'll move on. Thank you very much.
yes, this is the first one. Yes. The other is the post one. So how do I use this? Just here. Okay. So I should stand here. Shouldn't move. So hello, everyone. I think that you all know me because I was bombarding you with emails, but I am Miroslav Merz. And my favorite topic are symbiotic binaries, and that would be the topic of this talk. I will tell you how to use the Gaia Science alerts to search for them. That would be the most important ingredient of this talk. But first, given that symbiotics were not mentioned at this meeting, and it's a very interesting group of objects, I will try to introduce them quickly. So these are interacting binaries consisting of a red giant donor and the white dwarf or neutron star crater with a lot of things going on a very wide orbit. So I say it's hundreds of days, the orbital periods, but it can go up to tens of years, and you still see the interaction. And because of this interaction, this sketch here is very, very simplified. So actually, the environment and spectra and variability of symbiotic stars is much more complex than what you see here. And I will not tell much more about symbiotics itself. You can read my review from this year. But I will show you how complex they are with one of the very good examples is our Aquarii here, because this one is close. So we can actually resolve these beautiful thingies that are all around. It's the material that is lost by the giant, but there are jets. So there is some evidence of the previous outburst, and there is something connected with the periastron passage in this one, for example. So you see that it's much more complex than the sketch that I had in the previous slide. And also the photometry is complex. And given that I will be talking now in relation with Gaia Science alerts, so I am not showing the spectra, I'm showing the photometry. And this is a long-term photometry because symbiotics, given the orbital periods, you need the long-term data. So this is 30 years for several symbiotic stars. And you see that not the single symbiotic star light curve is same as the of the other one. And it's also that if you take one of these examples, you see that the way how they behave changes. So there is a lot of related to orbital, which you can see like these waves here, but there is also a lot of outburst activity. There are eclipses in some of the systems, so it's very complex. And you can use this variability, especially the outburst, and this is the way how it was done in past, to search for new symbiotics or discover them. Because if there is something in an outburst, then observers can easily notice that something is going on, and then you can find new symbiotics. And the reason why people still are searching for symbiotics, including myself, is that there is actually quite a large difference between what is predicted that we should see, the numbers of symbiotics in our galaxy, that's this. The spread is large, but anyway, if you compare that with the number of known symbiotics in our galaxy, there are still probably hundreds or tens of thousands or hundreds of thousands. I don't trust that numbers, but anyway, there are many to find. And Gaia Science Alerts, it might be one of the ways how to do that. There was an effort in Gaia DR3 to classify symbiotic stars based on the DR3 chunk of the light curves. So this was introduced already by Laurent yesterday. There was this machine learning classification, and symbiotics were one of the classes. But given that this was mostly based, this is a very short summary of the very extensive work, but these were based on the Gaia light curves and kind of a position in HR diagram. The problem is that then you can end up with a large contamination by pulsating giants. And we can talk in the discussion about that more. So what we did using Gaia DR3 data were to combine the variability with the emission information, because these are emission line stars. And Gaia actually reported equivalent width of H alpha. So here you see the distribution. It's in the negative numbers, which means in emission. And this is distribution for known symbiotics. So all known symbiotics are emitters, apart from a very few ones. So we combined the variability and this information with a bit of magic with infrared and so on. But anyway, we ended up with a sample of nice set of sources. We observed all of them. The majority actually is emitters, and they have M-type companions, which is what we were looking for. And with this and some other sample, which I'm not showing here, we already discovered about 60 new symbiotics, including 2 carbon symbiotics, which is rare because we have 10 in our galaxy, so it's nice. So it works well, but the main problem is that you need to set your threshold for picking up these emitters from this kind of low resolution BPRP spectra, or even if you are using, this is very similar for narrowband photometric surveys with H alpha, you need to set the threshold relatively high, because otherwise you're picking a lot of contaminants. For example, late type stars without emission look like they have something in H alpha region just because you have molecular bonds on both sides. So if you have these very late type stars, which a lot of donors is late type, then you will end up with a lot of contaminants if your threshold is low. So you are losing a lot of nice symbiotics just because you need to set the threshold high. And the other thing is that sometimes we saw that some symbiotics just don't show any emission before they outburst. So they are in accreting only stage, and then the symbiotic life is starting with the outburst. So this is one of the Gaia Science Alerts examples where you can see that there is nothing outside the outburst, but during outburst there is a very nice strong emission. So you can use these brightenings to search for symbiotics. You can use Gaia Science Alerts for that. Some of the brightenings are not only because of the outbursts. So some of these objects were alerted to be in kind of brightenings just because that was a maximum of a pulsation, or that was something related to orbital motion or so on. And here I just list a few Gaia Science Alerts which are related to known symbiotic stars. So there were some Gaia detections of known outbursts. And for example, this one is symbiotic recurrent nova, which actually there is just one point basically detected by Gaia in outburst. And then because the outburst is very fast. So even this can be very valuable. Then there is another example here. And for some of those, these were first ever detected outbursts of these objects. So they were observed only in quiescence before. And also, there is a record now of some symbiotic stars that were discovered thanks to Gaia Science Alerts. So I'm again not going through all these objects, but for example, this one, Gaia 18AEN, is the first symbiotic star discovered by Gaia. That's a paper from 2020, and a lot of you actually co-authored that paper. It was before Black Hole Tom, but the network was used for the follow-up. So you see that there is a lot of photometry we have from the follow-up network. But that was, the Black Hole Tom was not existing at that point. And there are some others. And this one is a very recent paper. It was accepted. I'm not the author of the paper, but it was accepted like a week ago. And it's very puzzling because it was confirmed that this is a symbiotic star. It was doing nothing, and then it dropped in brightness, and then it went into the outburst, and then it dropped in brightness even more. So below the quiescence level, and it's not clear what is causing that behavior. So there are very weird symbiotics that you can actually discover. So then the question is if we can find more than what I showed you on this slide among these $27,000 from Gaia. And the statistics were given by Simon already, but there is a lot of supernovae, there is a lot of PSO, CVs, novae, but there is a lot of unknown objects among the Gaia Science Alerts. As a spoiler alert here is that Gaia alerts are not particularly good for symbiotics for a very simple reason that there was a filter that tried to avoid these very red, high amplitude things, because then you will end up with a lot of Myras. So it still means that there might be a lot of variability, interesting variability changes related to known or unknown symbiotics that is missed in Gaia Science Alerts. And therefore, DR3 or DR4, 5 will be very interesting for symbiotic variability. But still, let's now try to search for some symbiotics within these 27,000 objects. So what I did was, first of all, this is the total number, and I was interested in the objects that have some historic magnitudes. The reason is simple. If they don't, they were very faint in quiescence, so I cannot tell anything about the quiescence appearance of the star if that was 25th magnitude. So yeah, there might be some real symbiotic missed because of this filter I applied. But anyway, you cannot really confirm them in quiescence anyway with what is available. So this is the distribution of this 12,000 objects in the historical magnitude. So there are some bright objects and there are a lot of faint objects. So then, given that we try to search for outbursts, then I filtered only those objects that were detected in brightenings. Actually, there was one known symbiotic detected in fading, and it was the first ever eclipse of this symbiotic star observed. So it was very interesting. But here, let's search for outbursts. So this is again the distribution of the magnitude difference from historical to the outburst one. And what you see, like this part, I ignored because that means that it that we saw the drop in brightness. So I was interested in the increase of brightness. And then, given that you have a red giant, then you expect to have a bright infrared source, which is the case for symbiotics. So therefore, I cross-matched it with the TUMAS to search for near infrared counterparts, and this is the number of the near infrared counterparts. And then there are some specific regions in color diagrams that symbiotics occupy. So we got rid of half of them just because they are not positioned well. 2,500 is a big number, and there are people who use infrared colors to pick up candidates, which I think is good, but it's not enough because these 2,500 objects are definitely not all symbiotics, and that you can see when I place them in the color magnitude diagram. So this is just to give you the idea where the features are on the color magnitude diagram. So there are white dwarfs here, main sequence, and red giants. And the objects, these 2,500 objects, is located like that. So surely not all of them are symbiotic stars. So actually, S-type symbiotic stars, this is the density. It looks better on the screens than on this main one. But this is where the known symbiotic stars are located. So of course, given that they host the red giants, which is dominating in the Gaia bands, with some comments on that, we can discuss that later. But they would be located here. So what then you can do with this kind of sample is to really focus on those that are located in the correct part of HR diagram. So when you are conservative enough, then this would be the region of interest. And actually, then you will end up with about 120 that lie in the symbiotic kind of region of the color magnitude, Gaia color magnitude diagram. So 120 is a much more reasonable number than this one, especially if you then want to check object by object, if that can be a symbiotic star. So what you see here is for this 120, the distribution of the historic magnitude. So there are some bright ones. And it's also the amplitude of it's not the amplitude of the outburst, but it's the amplitude where it was alerted. But there are some with very small amplitudes and some with very huge changes, let's say. So when then I took a look at this sample of this 120, so what I found is that, first of all, this method is not good for extragalactic objects. We lost some in M31, and even my own discovery in M31 with Gaia alerts. This is not in this sample, just because the 2-mass counterpart is very faint, because it's far. We lost also some D-type symbiotic stars. So that what I was showing and what is here in yellow are S-type symbiotic stars, which means stellar. So the optical is dominated by the stellar spectrum. But there are some with Mira donors that produce a lot of dust. So they are very, they look like planetary nebulae in the optical. And they have the infrared excess. And you see them, these brown, reddish brown objects here. And they also lie because of some reasons in other parts of HR diagram. So if you just focus on this region, then you lose them. So I know that I lost some of them, the known ones as well. So then what is remaining in the sample is a bit of contamination from the pulsating stars, again, because we are not selecting particular type of variability detected by Gaia Science alerts. There are actually micro-lensing candidates in this box, which probably Lukács group already classified, because they can be, on that part of HR diagram if the lens is a giant, and then they are in my sample. And maybe a few of ISOs, AGNs, Arcor and Borealis stars, which are the deepers, but some of them were actually alerted by Gaia when they were going up from the deep. So there is still some contamination in that. So it's not like 120 symbiotics, but there are several good ones, which can be then confirmed spectroscopically, and we'll have a nice sample. But that will be for some other Gaia Science Alerts meetings, because we need to do spectroscopic follow-up. One thing that may help to narrow down, apart from the eyeballing of that, and that would be the last message I will say, is that there is this value of historical scatter. So what was happening before the Gaia alerts? And actually, we know that symbiotics show a lot of variability. So those are the proper symbiotics would probably lie in this region, not in this very nothing doing region of the band. And with that, I will be happy to take the questions.
Thank you very much for a thrilling talk. We look forward to the spectra. Do we have questions, please? Łukasz.
So I'll be asking this question to different science cases. So what is your dream follow-up strategy and your advice to the telescope network if you find to satisfy your science?
So first of all, at this kind of stage of every search for symbiotics, you need spectroscopic follow-up, not necessarily high resolution. So what you are looking for is actually the red giant spectrum with emission lines, and you can see them in low resolution as well. So like you can go for 500 or so. So you don't need, and you want to cover as much of the optical as possible, because then you can do some ratios and so on. So that would be the first step. The other thing that you want to do is then to characterize them a bit, if they are symbiotic indeed. So there are different ways, for example, how people obtain orbital periods, because that's one of these are binaries, so that's one of the parameters that you want to have. From photometry is quite complicated, especially if you have one color, which is case for most of the surveys, because the orbital motion is dominant somewhere in the blue region, while in red, it's the giant pulsation that dominates. And actually in Gaia, you can see that well, that it can be a mix of the two. So the multicolor follow-up, but the problem of these objects is that you really need to do that for years. And multi-epoch high-resolution spectroscopy for RVs is also something that you want to have in the ideal world, right?
I have a question too, which is there are light curve photometry for everything in DR3 that's classified as variable. Have you explored those to look for signatures?
So not like taking all stars and trying to search for symbiotics, but I was working with symbiotic light curves, so of known symbiotics. The thing is that it's still a bit too short. Given the orbital periods, you have one orbit or 1.5 covered. So it's a good, something like to show what you can expect with DR4. And that would be much better.
That was my follow-up, yeah. So DR4 will give you a much longer baseline and you get the epoch spectroscopy. So that could be very valuable. If you can train to look for them, something that grows in H-alpha especially would be a fantastic signature. Okay, if there are no more questions.
Josh,
Hi, Josh, go ahead.
Yeah, I mean, if you have a list of symbiotic stars, I would very much like to get it. I can give you 3 colors RBI every night.
Yeah, I need that for 10 years, but sure.
Okay.
You don't ask for much.
It's one. Don't worry, I'm not going anywhere. I'm giving a post-it talk just after this one.
We have time, Mariusz, so go ahead.
So I would like ask you if you plan to release the new catalog, because the last one I think is the Belczyński catalog from 2002. I'm right?
No, I have my new online database of symbiotic variables, which is public. It's online.
Okay.
So that's the updated list. There was a first release in 2019. That's a short research note, but now I have a paper in under review for like a proper catalog paper. Yeah.
Okay. So I don't know because I'm not referee of this paper. Sorry.
Yeah. I don't know who the referee of the paper is, but there is some discussion that will need to be taken.
I guarantee it's not Mariusz, based on that question.
Yeah.
Now we have to rush on to the next really important talk. So
will you switch to that one?
We're going to switch, Jaroslav, to talk number 2.
So yes. So this would be more related to black hole Tom, actually. And it is the famous T Corona Borealis, the object I didn't want to get involved with. And I ended up writing a paper on that. So you know that this is a symbiotic recurrent nova. Symbiotic because you have a red giant donor and a white dwarf accretor, which is it's showing the classical nova outburst. There are not many recurrent novae known in our galaxy, just 11. And out of those, 4 are symbiotic with the red giant donor. The rest are classical with the red dwarf donor, main sequence donor. What is interesting about the recurrent novae is that they have recurrent outbursts, which in symbiotic novae, we know that those have a very massive white dwarfs. So it's very interesting. In this case, it's quite close to Chandrasekhar, actually. And the red giant is filling the Roche slope here. And if you will at least take a look on those last 2 well-recorded eruptions, 66, 46, 26, right? 80 years. So we are all expecting that this one will appear as in outburst soon. The thing is that it's not that simple. So this is Arizov-Yuhi, another symbiotic recurrent nova. So you see how actually this is well behaving. Not really. So you cannot expect this to be very regular because you have a red giant donor and the mass transfer from a red giant is not very regular. But anyway, people claim this, we will see that soon. And it's not only the 80 years, but it's also because there were some similarities observed before the previous outbursts in 46 and now. And it's, for example, this super active stage, which was observed, and then some dip in the light curve that people claim this is indicator of the imminent nova eruption, which we have studied in this paper with data from AFSO. What you can see here is very nicely covered, and with black hole TOM. And the result, the scientific result of the paper is that this is not a good indicator. So we might see this outburst next Wednesday or tomorrow or in a year or in two. It will happen. As we discussion with Lukasz we had, it will happen, but I cannot guarantee that we will have this indicator like, okay, prepare next week, there is an eruption. So if you will see these papers, there was a research note on that it will happen on that day. So no, you cannot trust those. So it can happen anytime and without any clear precursors. And it will be one of the brightest transient seen in decades. The outburst is very fast. We have already heard that. Even how fast it's evolving, but also the optically is very fast. So by 2, 3, and 6 magnitudes, it's between 3, 5, and 12 days. So in 12 days, in 2 weeks, you are gone from the sky. But it will be very scientifically interesting object. Not only because how fast, how bright it will be, but for example, there is this secondary dip, which might be because of the irradiation of the red giant, but we will need a spectroscopy for that. So there is still a lot of science that we can learn from that. But this is something which we actually included in the paper. The public should be careful about how amazing this performance will be, and we as astronomers should communicate it clearly, because these are titles also from BBC and Forbes actually about this spectacular biggest sky event for 79 years. And what is more dangerous in my view is that actually there is a channel, it's called NASA Space News, which has nothing to do with NASA actually, showing that it will look like this, which I consider myself a bit of expert on these things, and I don't think that it will look like that. So actually what you will see, it will look more like this. So have you noticed? So this is T-Corbor. So this is in quiescence, and this is in the outburst. So it will be like Polaris. So it's super exciting for astrophysics, but we need to be careful how we communicate this with public, and that's my message from this. I don't need 1 more minute to repeat that, but this is one of the messages. We are astrophysicists, we are astronomers. We need to communicate clearly how exciting that would be and what people will actually see, because that's what they will see. If you want to know more on the work, there is a paper that we published in Monthly Notices Letters. Thank you.
We have time for a question. Please go ahead.
Do you have any suggestion if the explosion will happen, how to observe? I mean, the problem with comparison stars, field of view, filters, and so on.
Yeah, sure. It would be a problem. Yeah, it will be very bright. So, for example, it will not only be problem in optical for CCDs. Sure, I can imagine that at the very maximum, when it will be magnitude 2, it will be really hard to do photometry. Black hole TOM would need to do the best what black hole TOM can do, no? But also, for example, it will be that in X-rays, it will be impossible to observe in the maximum because it will be just too bright. So it's not the best symbiotic recurrent nova that you can wish for. It's just too bright.
We had another question here. Jeremy? No, there was a question here somewhere. Okay, then Michel, please.
Thank you. I would just like to remind you that one of my colleagues, Jean Schneider from Paris Observatory, has made an analysis to try to interpret the quasi-periodicity of 80 years. And his claim is that it should be a three-body object. And with that hypothesis, he can predict when would be the next eruption, if this hypothesis is correct. And the next one should be around 10th of November, if I remember correctly. There was one prediction in March we did not realize.
Okay. Nicholas will laugh, but yes. I will probably not comment on this.
No, but the problem is that now, as end of September, the object is practically not observable anymore for the next few months. So if it's effectively reaching second magnitude, it could be observed in twilight in November. So we have to be careful and have a look at the sky before the night is dark.
Yeah, I would be very, very careful about predicting, this kind of event in a symbiotic system with a mass transfer from a giant that is doing what the giant wants, not what we want, to a particular day. So.
Michelle, use microphone, please.
Yes. For a two-body system, I would agree, but his claim is it's a three-body system. I cannot say whether it's true or not, but.
Sorry, can we use microphones? And we have 2 more questions and we have a coffee break. We have 3 more questions. So the 4 more questions, lots more questions. Wow, you.
It's an interesting object.
No, this is not a question, just a comment that well,
So
it is
keep
an
it rapid,
advert.
please.
At the Nordic telescope, we have diffuser, so you can observe very bright targets because the PSF is diffused to several arc seconds. So
beautiful, good news. We're going to run over a little bit into coffee because I think it's good to have discussion. So let's carry on. So the next question was here with Nadia at the back, please.
So I'm very intrigued that this is so close to the Chandrasekhar mass, and I'm wondering if based on your previous talks, what, if any, optical light curve features are correlated with mass at all, and whether you can identify neutron star versus white dwarf accretors just from the light curve without the X-rays?
I'm not sure. From light curves, probably not. What you can use is the optical spectrum, kind of, because those with this nice emission lines, those well-behaving symbiotic stars, we call them shell-burning symbiotic stars. They have plenty of really nice emission lines in optical, and this is because there is a layer on the white dwarf that is like burning the material, so that you don't have on the neutron star. But then I'm not sure if without X-rays you can tell if you have a neutron star symbiotic or the accreting only, how it is called, symbiotic star with a white dwarf. That I'm not sure if you can tell. With the mass, one good indicator is actually how frequent and how fast the outbursts are, if these are nova type outbursts, so thermonuclear runaway. Because on the in symbiotics, which are not that massive, the outbursts are ongoing for very long. They are very slow. In symbiotic recurrent novae, this 4, the outburst is super fast, and it's because all these 4 have very massive white dwarfs. So searching for those, that's a project that actually I started, is to search for novae with red giant donors that shows very fast outbursts, because those could have been with the massive white dwarfs. And at least to finish, at least with the RS of Yuki, we know that this is a CO white dwarf. CO white dwarf cannot be born with this mass, so it grows in mass because of the interaction. And it's close, so maybe that's a supernova 1A progenitor, but it's just a sample of 4 or 5 objects within this.
Thank you. We still have a poster talk, but there were 2 more questions. I'd like to do them with the conference organizers' permission.
Sure.
Please go ahead. There's it's just here in the white shirt. Thank you.
Thank you, Jakub Nurkiewicz from Astrophysics Student Club of Gdańsk University of Technology. I want to ask if there will be possible to detect neutrinos a few hours before that event.
I have no idea. That's so far from my wavelengths that, yep, that's maybe for those people back there, those are, the energies somewhere there.
Thank you. Thank you. Laurent.
Yes, given the visibility of this star and also the different telescopes which are surveying the sky, not all the time, is there a risk we miss the outburst?
With the number of amateurs that are looking at this star, if this is observable, we'll not miss that, because like everyone is observing that. No, with the small telescopes, 5-centimeter telescopes. So if that will, but I think that there is not like really long period of time when it's really not observable. No, it's not for months. No, it's close to 0, I think. Yes.
You can argue over coffee, but let's have Timotheus, I think, is the next presentation of the day, please. Come on up, and thank you for your patience. Thank you for waiting. Let's thank Yaroslav for 2 talks. I'll give you a...
Okay. Everyone announced a coffee. So, as Katarina Bonkowska, my supervisor, said before, I'm working on analysis of the cataclysmal star X, which is really active star. Eduardo with Eduardo, and also the SU UMA, which means that it undergoes the super output except normal. So we measured the super cycle length using the geometric data as ZTF via BH-TOM and also with our own observations and the after observations. And we found then that in previous publications by Otulakowska-Hypta in 2015, the change which she calculated differs a lot with that one we calculated. And you can see that it differs by an order of magnitude. So it's something wrong with calculations. And the reason she get this result is of the small amount of data. And the other reason can be source. Precursors are the Nepal outputs before the church. That if you substitute amount of methods, they just cancel each other out. So it doesn't matter. So we're still waiting. Something interesting. It's not the linear fit. Maybe it's an experimental fit. But yeah, it's now we are just waiting. Thank you so much.
Thank you very much. We do have time for a question or two. Please.
Thank you. I was wondering the paper from 2013. So that was based only on the data from AABSO or?
No. We based like now the data from the AABSO was taken from 2020.
Yeah, so
more or less.
Since tests ZTF, BH-TOM, and also the data from the ABS are like from the time, do you know from on which data was the analysis from 2013?
Yeah, we know. Yeah, we know that it's just one super, so it wasn't really precisely, and it was made by Oleg, I think, in 2000. You can see on the graph like the blue points. They are the measurements from the previous publications. The first was in 1993, more or less. Something like this.
Okay, thanks, Tomek. My question is simple. Who's right? Otulakowska-Hypta or we?
We don't know yet. We find out, but something was wrong. We are waiting just for more measurements.
Thanks to the speaker. So now is time for coffee. We managed to overrun, even though we lost a talk of 30 minutes, but that's nice because we had lots of question interaction. So we see you back here at 4 o'clock. Thank you. Welcome back, everybody. As you're coming in, our first speaker is Agnieszka. I don't know if you're in the room. We've just got a small announcement before you speak, so but then you'll go up there. So I'm going to hand over to Miloš, who's got an announcement suggestion to make. So please pay attention.
Yeah, hello. I have a short question to everyone. Tomorrow, during the trip to Observatory, the idea emerged to go there and stay a little longer, not on the terrain of Observatory, but on the mountain, to see the night sky from there, and maybe do some astrophotography. We have like 4 people that are wanting to do it for now, but we need people with cars, so for it to work. So yeah, if anyone is interested, I would love to see hands. Yeah, sure, but like just to get idea. Yeah. All right. So, and people with cars. Who's all right? So we have 1 car at least. Okay, great. All right. So I think tomorrow there will be a list or something for this idea to happen. Thank you.
I don't know if you thought of using the Slack channel to re-advertise it, and maybe that might be a way to get people to contact you. Okay. All right. Thank you very much. And Agnieszka, thank you for your patience. I will give you a 5-minute warning.
Okay.
Polarimetry.
Thank you very much. Thank you very much for allowing me to present my my work. My name is Agnieszka Gurgul. I'm just starting my PhD tomorrow, and I'm also technical staff at the Institute of Astronomy of Nicolaus Copernicus University in Toruń. I'm working mostly with the telescopes, and as Basia already said, we are already do some work to automate one of the instruments in our institute. So I will show that. I want today to present some time domain polarimetry with 2 of the instruments. And so, yes, in our observing community, we are using many observational techniques to study starlight. The most commonly used, the photometry, to measure the intensity at different wavelengths. To go into the details, we are using the spectroscopy, but the information about the geometry and the symmetry of the light provides us the polarization. So the polarimetry gives us information not accessible otherwise. It's a complementary techniques to others. So I would like to present what we can achieve with that. And I believe polarimetry is still underexplored in time domain, mainly probably due to the lack of access to such instruments. And yeah, there are many other techniques, but yeah, as BH-Tom community, I will focus on this one. For those unfamiliar with polarimetry, as I know there is no academic courses, at least in Poland, about the polarimetry in most of the facilities. So polarimetry, like quick graphical interpretation of the photopolarimetric observation, we are probing light at the different transmission angles. So if we imagine light as a light beam, as a superposition of the single waves, like propagating it many directions, and we are looking through the line of sight, we are seeing the intensities and the amplitudes at the different levels. So if all the intensities at different angles are the same, we are saying that this is unpolarized light, that there is symmetrical. There is symmetry in the line. But if there is any change, if such intensities at different angles, the light is partially polarized. If there is like only one direction, so the light going through, for example, the linear polarizer, it's the linearly polarized light. Just by probing the different angles, the intensities, we can estimate so-called Stokes parameters from which we can get the polarization degree and the electric vector polarization angle, simply called polarization angle. And Yeah, these are the most commonly used polarimetric values. There are many different approaches and ways to measure polarization. We can adapt most of the telescopes to measure polarimetry by just putting the proper filters with dichroic ones, and by measuring these intensities in many different angles, we can increase the precision of the measurements. So I'd like to present our TN-Pol. It's Toruń N-polarizer polarimeter we are building in our second dome. This instrument consists of like the two optical tubes, the 20 centimeter and 35 centimeter. Both are dedicated for the time domain studies. One will be dedicated to photometric studies, second one to polarimetry fully. And we can switch the telescopes for these measurements depending on what we need. For example, like the more light from the larger tube, and we can do the simultaneous observations in both techniques. The instrument consists on the calcite Savart plate, which is dichroic crystals, giving us the images of the same star in two orthogonal polarization, and we will be using the rotating halfway plate to be able to rotate the transmission axis to probe it. Still, we have to examine at which angles we want to measure it. Usually it's like the minimum number of angles is 3 to be able to measure polarimetric signal. Usually it's like 4 angles by 45 degrees or even like 22.5. So it's still the way to explore. Due to our optical system, due to the coatings of the Savart plates, for us, we have like this wavelength range in which it transmits. So we will be limited to VRI bands. And the field of view, the effective field of view is around 30 arc minutes. We had the first light at the beginning of the August this year. So it's like pretty new instrument. We are still working on automation and the optimization of the working. With careful calibration on the polarimetric standard stars, we expect to get the precision on the level of 0.1, 0.2% in polarization degree and below 5 degrees in polarization angle. The second instrument I want to show, it's something which is here on Teide Observatory. I had privilege to work at one of the ESA projects called Neopol. It was dedicated for NEO observations, polarimetric, and we built the polarimeter for the 1 meter OGS telescopes we are going to visit. The first light of this instrument was in 2020 in the mid. And it was done in our institute at our 60 centimeter Cassegrain telescopes due to the COVID restrictions. So the first initial calibration campaign was there. The final calibration campaign on Teide, I came here at November 2022 when the restrictions were lifted. And I had only 5 nights with the great weather to do the calibration campaign. The design of these instruments is slightly different. There is a beam splitter at the beginning and 2 wedge double Wollaston prism, which also creates the 2 orthogonal polarization. But with the beam splitter, we get like 4 images of the same star at 4 different angles. So we are able to measure the Stokes parameters to get the polarization values just from 1 measurements. But it also limits us to the brightness of the stars because we are like dividing one star to 4 different images. This instrument operates with 2 bands, so with V and R. The field of view of just single stripe, as you can see, is around 1 per 10 arc minutes, and the precision is like presented here. But as I said, it was only 5 days, and I believe with longer period we would have like much better results. Yeah, I hope we can see it. The results from the calibration will be published in a paper. I did some observation for the stars with debris disk, and also the calibration of the Neopole will be presented there. In general, the polarimetry gives us information about the symmetry of the light. So most of the stars are spherically symmetric. The net polarization is close to zero, but there are multiple mechanisms causing polarization. The common one is the scattering of light of stellar atmospheres, the circumstellar matter, circumstellar disks. And a few years ago, Łukasz introduced me with the topic of the simulated analysis for the polarimetric studies of microlensing events. And in gravitational microlensing, symmetry is broken due to magnification of the different part of the source, causing change in the polarization signal. The maximum polarization is depending if it's like binary or single lens. It produces usually like 2 peaks with maximum polarization at limb due to the limb darkening. So it magnifies only selected part of the source, like causing break in the symmetry. Microlensing of stellar photosphere for main sequence stars, we expect lower value of net polarization, so below 0.1%, sometimes 0.2 I found in literature, but for the stars with extensive envelopes, like the red giant stars with extended envelopes, there is expected to be much higher signal and level of polarization, even up to 10%. The combination, the observations, photometric and polarimetric observation determines the less impact parameters. So it gives us some already information, and the variation of the polarization. So not only value, but the change in time can determines both the magnitude and direction of relative proper motion. So during the literature review, I found the information from 2015 based on the OGLE-3 data, that for over 4% of high magnification microlensing events, the polarization is enough, like it could be enhanced with the amount of about 1%. And as we found, there was in this data over 4,000 of microlensing events, so still we will expect to be able to detect the polarization signal for over hundreds of such events. I did some simple simulation, as I'm not working with the microlensing events. The polarimetry for single lens transiting, so it creates double peak with the maximum local polarization at stellar limb at 3% for the giant star with larger atmosphere envelope, and smaller polarization for the main sequence stars to estimate what can be seen, and if we are able to detect it with such small telescopes, but with full time access. And yeah, we have here the curves. The produced polarization for giant star is as we expected. It's pretty much higher, but what can be easily visible, the polarization angle rotates drastically during the single lens event. So it gives us model independent and clean microlensing indication. Also to detect, to estimate the detectability for polarization of such telescopes, I did some math, and there is in the table the estimation of the integration time needed to obtain such polarization values for different size of telescopes, which we were using at some point. So here we expect to be able to see the bright polarization, bright microlensing events up to 13, 14 magnitudes. So maybe we will be able to observe something, some microlenses from our BH TOM. And yeah, here I will have a small announcement and an example. As we are here, the community, most of us, the community from BHTOM, I hope you already know this eclipsing binary, EESFA, and I hope it's on your observing list. It's pretty bright. Eclipsing binary disk occurring system. So during each eclipse, it's changed a little bit. The previous eclipse was in 2020, and there is pretty nice light curve, a photometric light curve, both from AFSO and from BHTOM. And the next eclipse is next month. So I really hope you will observe it. We had the polarization curve also from that previous eclipse from Mount Suchora Observatory. They are using the two Savart plates rotated by 45 degrees to measure. I will not go into the details of the interpretation of the data, but you can see clearly that there is a variation in the polarization signal. So we are also willing to observe it this year and observe it both photometrically and polarimetrically. And I encourage you to do the same, especially if you have polarimeters. I believe it's a powerful technique to detect so many signs. And to summarize my talk, polarimetry is powerful, but still underutilized technique, especially in time domain. The access to the polarimeters, even the small ones, can bring us sensitivity and cadence to time domain studies. We know that applying for time for larger telescopes, which are equipped with the polarimeters, it's really hard, and especially with microlensing events, we cannot predict this, so the follow-up studies. And for microlensing, we have the polarimetry provide additional independent source of information, which can help us with the modeling of the source. So now we are planning to integrate these instruments in the network alert networks, so BHTOM, to be able to be part of the routine follow-up studies. Thank you very much for your attention.
So we have time for one quick question. I'll ask one. A few slides ago, you just showed us the sensitivity of the as a function of magnitude and the mirror diameter, so which is pretty useful. So so I just want to make sure I've interpreted. This is the signal to noise.
No, the signal to noise is like we wanted to be able to detect polarization, like 0.5% polarization with 3 sigma. For this these diameters, I use like pretty. I use the throughput for the telescopes on the level of 1/4, like for the Neopol, like we have like from 1 star image, we have divided the light for 4 parts. So it's really careful. So still, I believe with the 86 minutes, so it's 1.5 hour, we'll be able to reach such magnitudes.
So it's the integration time to reach your goals, 3.5, 3% or 0.5%.
Yeah. Yes, this is
in
0.5%.
0.5% in 3.5 minutes on a 1 meter, which is pretty good. A question from the back. No.
In the eclipsing binary, what's the mechanism of polarization? Is it some sort of scattering in you said there's a disk?
Especially for this target, there is a disk. So this is this occulting system. The interpretation of this, I would not like to go into the details because it's not my work yet. I'm planning to do the observation this year, but I know this eclipsing binary is pretty well studied, and we know that there is a disk. So every eclipse is a little bit changing, and it gives us information about the disk. Like the mechanism in the disks are like different due to the different size of the grains, the cavities, and so on. So yeah. We will see after the eclipse. I will make some more work on this target.
Thank you very much.
Thank you.
So let's thank our speaker and invite the next speaker up, please. Hi, thank you. So I'll give you a 5-minute warning. And the advice is not stand too close to the microphone because it will get boomy. Please take it away.
Okay. Well, we can start. Hello, everyone. Thank you for the opportunity to give you today a talk. My name is Eugenii Stefanenko, and I'm from Astronomical Observatory of Jagiellonian University from Poland. I'm the second-year master student. And continuing the topic of polarimetry, I would like to say a few words about time domain polarimetry with BHTOM, which can be done with BHTOM. By BHTOM here, I try to emphasize the small and medium-sized telescopes, and I would like to, and I will talk about them today mainly, and give some scientific potential and technical implementation of such observations. Here is the outline of my presentation. I want to start with some general thoughts about polarimetry, why it is an important technique today. Then, as an illustrative example of such observations, we can show cataclysmic variables, and I will tell why the polarimetry matters in such kind of objects. And next, the vast majority of my presentation I want to spend on design of a simple polarimeter. I mean, not simple, and not the most simple, which we can use in telescopes. That's because most of the BHTOM telescopes which are participating in this network are not currently equipped with the polarimeters. So maybe one will want to. And after I will end with simulation of the polarimetric output, and we will see how it will go. In general, polarimetry is the measurement of the polarization of light, as been said. Most of the stars, if we're talking about stars, are unpolarized. And even a few of them are polarized, the degree of polarization is usually small. Here I just added some nice pictures and examples. On the left, you can see the, some AGB stars and dust around them, which probably polarize the light. On the right, Jupiter and its magnetic field, which also can polarize the light. In the middle is a known picture of M87 black hole, and the disk is also polarized. But today, I would like to focus on magnetic cataclysmic variables as an illustrative example for polarization. We call them sometimes prototype IM Hercules star, or if the magnetic field is strong enough. As a cartoon, you can see on the right, if the magnetic field is a white dwarf is highly magnetized, it could prevent the formation of accretion disk, and we will end up with only one accretion column, and the shock region will occur. But what is important to my topic today is that the important feature of this object is a highly polarized circular light, which the mechanism of this emission is, if this polarization is a cyclotron emission. You can see on the left some examples of known polars, and the degree of polarization, circular polarization, V-Stokes, is even 15 to 20%, which is quite a lot. So suppose we have a target of interest. I will back to it later. Now we can briefly discuss and some instructions how to start metric observations. And first thing which is needed to be carefully is the choice of the telescope system, since every obliquous incidence on a mirror changes the state of polarization. It produces two effects, namely the attenuation, which is a polarizing action, and retardation, which is a wave plate action. So we want to minimize it, and one can show that rotationally symmetric systems show little or near zero instrumental polarization. For example, Cassegrain, Gregorian, or prime focus systems will have this small instrumental polarization, and asymmetric systems like Kudo or Nasmith will generally possess strong instrumental polarization. When this is done, we can move on to general setup of polarimeter. We have three general elements we need to put here. It is modulator, analyzer, and detector. I will start with the analyzer, since this is the core of the polarimeter. We have multiple options here. We can start with linear polarizer, and it can be the most simple options like the heroic sheet polarizers. They are simple and cheap. However, they are able to provide only single beam polarimetry. So we will lose half of the photons, which is not very good for the faint objects. So today astronomy is mainly focuses by polarimetric observations on the dual beam polarimetry or more beams, like prisms, Wollaston, Savart plates, and other prisms. Wollaston and Savart plates are surely the most common solutions. They enable us to simultaneously measure two orthogonal states of polarization. Yeah, this is the idea. I also wanted to show some examples of known and nice working polarimeters, a RoboPol instrument, which is mounted on 1.3 meter telescope. It uses double Wollaston without wedges, however, which is a technical detail, but it enables us to measure simultaneously 4 states of polarization. So it's also nice. And the big problem which we can find with this Wollaston prism and Savart plate is lateral chromatism, which is a problem. It's very sensitive to the wavelength, this separation angle, and it can be solved with use of these two chemical compounds. You can see in the bottom right. On the left is quite expensive option. However, magnesium fluoride is quite accessible and usable option. More often than not, a polarimeter contains a modulator. In order not to rotate entire instrument, we can only include modulator into the polarimeter. And mechanically stable and nice solutions is rotatable half wave plate or quarter wave plate. They are commonly used. However, there are also some modern and expensive solutions like photoelastic modulators or ferroelectric liquid crystals. And the latter is, for example, used on the mini HIPPY instrument, which is, by the way, mounted on 35 centimeter telescope, provide really nice polarimetric data, which is quite impressive. Ending with the detector, general requirements for detectors are the same as for photometry. We want to have large quantum efficiency, low readout noise, low dark lines, high linearity. I also here tried to write some examples of polarimeters mounted on small telescopes, because those are which I was mainly inspired by preparing this presentation. Some of them are more for teaching purposes even, but some of them provide real and scientific data. And as you remember, I mentioned only magnetic cataclysmic variables, but of course it's much more. Much more sources we can observe. We have supernovas, blazars, and dust grains, our galaxy, and they are all accessible and reachable by the small and medium-sized telescope. So we can find here is a great potential for them. And the final thing I wanted to show is some simulation. So to test this hypothesis, either it can be observed with, and how it can be observed with a small telescope, I tried to prepare a simulation. It is done by HCI Pi open code, written in Python. It is generally enable us to simulate the optical elements and the wavefront, and propagate the wavefront through these optical elements. So we can, in some sense, try to measure the polarization, for example. Here I included some quarter wave plate and dual beam analyzer. As a reference telescope for my simulation, I chose the telescope from my home institution, CDK 500. So you can see here all the parameters, half meter diameter, etc. Here is two important assumptions in this simulation. I need to mention. I also only include photon noise and readout noise as two noises. Well, of course, there is much more. And the second assumption is I assumed nearly perfect calibration. So the flat field, dark current are perfectly calibrated. And so we can see what is the result. Important feature you can see on the top right here is the Airy patterns, which were calculated for every point for every quarter wave plate position. They are deformated. They are not like nice Airy patterns, but deformated by the seeing. And here comes the important feature of the dual beam polarimetry. Since we will calculate the subtraction of these two images, all the atmospheric conditions, they're the same, and this is important. We can see that in these two beams, the forms of deformation is the same. they'll just cancel by subtraction. And this is important. In dual beam polarimetry, we can cancel these atmospheric effects. So I tried to simulate very simple kind of polar, like 15 magnitudes, 3 hours period, and magnetic field strengths from 20 to 30 megagauss. And you can see here the result from one night, only one night of observation. Error bars were also calculated in a simple way from Poisson distribution, etc. We can see that even now the results are not bad, but maybe it will be challenging to recreate the entire curve from this result. However, if we have 7 nights of simulation and if we will average out all the measurements, also I assume 7 nights of nearly perfect simulations observations, we end up with this curve and with this result, which is also looking nice. So to sum up and to conclude a bit, I wanted to say that getting started polarimetric observation is challenging for sure and calibration heavy. And didn't include here the calibration processes since I assume that they are near perfect. But they are for sure repeatable once they are set. The smaller telescopes are also limited to 16 to 17 magnitude in polarimetry, and this limit came only from my simulation, and for sure it will be different from telescope to telescope, because we need to remember that we want both beams to be visible enough. Both beams we want to then do photometry and to measure how much light we have. But of course, in the end, science wins. With polarimetry, we can have some unique constraints on magnetic fields in the universe, in every object of interest, and geometry of many objects of our interest. And this is all for me. Thank you.
I'm going to jump in and follow up on something you just said, which I hadn't thought about before. Do you have astrophysical sources you can use to calibrate the polarimetry?
Yes, we have. I also here inputted some calibration unit. I didn't say a word about it. For sure, it could be any known polarized and or unpolarized star. And there are catalogs of those known stars. So yeah.
Question here, Dave.
As someone who's been doing polarimetry for 30 years, it's great to see some talks promoting polarimetry. Of course, as you pointed out, there's lots of instruments that have come online or will soon come online. I just want to make a comment about the issue of rotating wave plates. As you probably know, if you're doing that at a fairly low at a low speed, then you run the risk of not making a simultaneous observation of all the Stokes parameters at one time. So for the instrument that we use in South Africa, we have a fast rotating wave plates, 2 of them actually, 1/4 at 10 hertz. And in that manner, you're able to get all Stokes parameters simultaneously, but that requires a detector that can work fast. So a lot of the newer instruments are not taking that sort of approach because, of course, they're not so interested in high time variability in the polarization. But for magnetic CVs, that's really quite an important thing that should be considered when you come to design a polarimeter.
Yeah, recommend.
No more questions? Here's a question. I can't see who. Nadia.
Oh, this is great. Yeah. So my question is for transients because they do change, right? Here you had like several nights, so you could accumulate your signal to noise. So then you said you're limited to 16, 17, but I guess for transients, which are like single epoch, then you are limited to a much brighter magnitudes.
Yeah, for sure it's a problem for smaller it's a limitation of a smaller telescope. It surely is a magnitude, and sometimes we are even ending up with 14 magnitudes, for example, for only one night observation. So it should be surely considered, and smaller telescope will be limited for this magnitude, but even with such data, science can be done. So it's.
Thank you very much. Let's thank our speaker again. So the next two talks are online. The first one is Diana, if I remember correctly. So Diana, you ought to be able to share your screen and we can see you. Let's see if we can hear you.
Okay, do you hear me?
We can hear you.
Okay, thank you. And do you can see the presentation here?
Yes, we can see your presentation.
Okay, thank
I
you.
have no way to easily tell you that you have 5 minutes left, so I'm going to hope that you can keep to time on your own time. Thank you very much.
Okay. Thank you for an opportunity to present our work at such an event. And my name is Diana, and I'm a student at Astronomy and Space Physics Department at Taras Shevchenko National University of Kyiv. And I want to talk today about using BH-TOM facility for cataclysmic variables classification. We would like to start with a short historical description of Gaia alerts. It's well known that the whole list of Gaia alerts consists of a little bit more than 27,000 of objects. The first alerted object was done in 2014, and the last one in January 2025. On the initial website of web page of Gaia alerts, there are some fields that can indicate type of object. Among them are class and the type of transit event determined when the object was published, and comment. It's additional information that may contain classification suggestion. And among all Gaia alerts, the initial distribution was such as here. Interesting for us was that a little bit more than 19,000 objects are still unknown, and around 800 objects are cataclysmic variables, which are very interesting for us. So only around 30% are classified. We began with Gaia alert list, and from this list, only non-classified objects were extracted within their magnitudes and coordinates. And our goal was to search for already known objects. We performed a cone search within 1 arcsecond radius. And first we used Simbad astronomical database, and approximately 4,000 objects were detected through this method. Next, we used a southern catalog of variable stars. As a result, approximately the same count was identified. Then also we use Twiki transient facility and Levear database for searching corresponding ZTF matches, and approximately 6,000 of objects were extracted in such method. And next step, we search for such objects in TESS input catalog, and we have found almost 8,000 of objects. So after cross-matching, almost 9,000 of unique objects were without matches. And now we are working at final classification of them and checking each of them individually. Some interesting objects for all follow-up observations can be added to BH-TOM. During each night of our observation, we need to check a huge database and a huge list of objects to reviewing the photometry data almost every night and decide, do we need to observe them or not? To make this procedure easier, without reviewing photometry, we have decided to create some alerting system that will alarm us for observations. And we wrote a program that downloads photometry data every night, every day for some interesting for us object from beach tombs. And will send us a message, do we need to observe it or not? We take into account a lot of factors, depends on behavior of object, like time of last observation, last magnitude. If it's not enough for our telescope, we will not observe it, or if it's all bright, we need to do it. Next step was counting dynamics of object. If we have seen already new flash a few days ago, or we are waiting for new flash, it's also worth to observe it. Or even better, if there are some oscillations of flux during the flash, we need to observe it longer. Or if magnitude peaks last for a little bit more than usual peak, it may be interesting, or there are some oscillation. We also need to observe that. And here our alarming system noticed that one of the objects we are interested in got brighter on September 16. This brightening was detected by ZTF and Atlas. Light curve of this object is quite interesting. We can see periodically or quasi-periodically change of magnitude with a similar character of peaks. And a little bit about objects SU. A characteristic features of such stars of this type is presence of two type of layers. Normal, its frequent show duration peaks with amplitudes around 1-2 magnitudes, so it's asymmetric profile with rapid raise around 1 day and slower decay about 2-4 days. And superflames, it's like a little bit brighter by 2 magnitudes than normal, and they're around 5 times longer than normal. And during these super outbursts, the light curve shows superposed periodical oscillations. It's called super humps, and their periods are close to the orbital ones with an amplitude around 0.2, 0.3 magnitude. And here we can see the light curve of this object in BH tomes. Both scale for time in both images are the same. So Gaia 23 BCB is one of such object, maybe one of such objects that can be classified as UMA stars. And here are presented 2 types of outburst. However, there were no such data of presence of super humps during longer outburst. So our alarming system gave us a message that we need to observe, but there were bad weather during this time. So we asked our colleagues to observe, and after we got the data, we make a long scale periodigram analysis, and we found periodical oscillation with a period as mentioned here. It's approximately 0.068 days, and amplitude of magnitude 0.33 magnitude. Periodogram, light curve, and phase curve are demonstrated at such slide. We have published our results in the Astronomer's Telegram about the first detection of super humps and estimation of their amplitude and period. See it here. Here, after a lot of our colleagues and our observation were done, light curve are presented here. The profile of light curves may seem not static, but it can be due to different filters. The amplitude varies about 0.1 magnitude, and the period is mostly stable. There are small oscillation within the error. Our program still sends us message to continue observations. So in September 1820, we got such light curve with magnitude amplitude 0.3 in all cases. We have also uploaded this data into BH-TOMS as demonstrated here. Further observations are also presented here. The profile, it cannot be said that profile changes during time. According to this data, we can conclude that this object is currently undergoing a super outburst with previously correctly classified as SU UMA type dwarf nova. And also we continue observation by ourselves and our amplitude of oscillation changed a little bit around 0.2, 0.3 magnitude, but period remained stable. To determine the optimal period, we constructed O-3 diagram, and to identify the value of period, we find the best value of period in such way. We find the value with which the highest point in the minimum value point was minimized, and the best period is here. It may seem that it's a little bit changed, but for that we plot period versus time of observation, and it may be not. It may be a little bit in increasing trend, but it's within. But suggestion, uncertainty is really too large to draw any meaningful conclusions about the changing of period. Additionally, based on data collection from Gaia alert list within their coordinates and magnitudes, we have generated a series of images corresponding to the relative position of objects. Each image continue a large square with field of view of 40 arc minutes and inner square 30 arc minutes, which corresponds to our camera. We use interesting is some fields of view includes more than 20 objects, so it may be very useful when we need to observe some object and other objects are inside the field of view. We can do photometry at the same time. And it may be useful for after photometry processing of images. Okay. To summarize, we used BH-TOMS facility to monitor, alert, and classify some cataclysmic variables like Gaia 23 BCB. We determined its periods using Lom's-Curve periodogram, and as well as amplitude of oscillations. We have estimated periods, and we cannot say anything about trends because of uncertainty. Also, we did cross-matching with other catalogs, and our system allow us to respond very quickly on some rapid brightness of objects, and to find more data about objects to classify them and just make bigger data base. Okay, we also want to thank to Waldemar and Nazli for making observations, making a lot of photometry observations for us, and BH-TOMS space. And thank you for attention.
Thank you very much. I throw the floor open to questions. Do we have any questions? I see a question. Łukasz, please go ahead. Microphone is coming.
Hi, Łukasz Wyrzykowski. This is great. So I really like the idea of alerts within the alerts. And I think you should somehow spread this information, maybe using our mailing list or something like that, because I think there would be many more people interested in contributing to observing your alerts on the alerts.
Yeah, sure, of course.
I don't see any more hands up. So thank you very, very much, Diana. Thanks for your presentation.
Okay, thank you.
So our last speaker of the day will be Josh Hamst. And I hope you can share your slides, Josh.
Hi.
We can see you.
Okay.
Slides.
Yeah, thank you for giving me the opportunity to present Road. And hi from Belgium, where I live. Road is my remote observatory in the Atacama Desert. I'm a retired nuclear physicist and amateur astronomer, a member of different organizations in Europe and in the US, the Flemish Organization of Astronomical Association, the AVSO, the BFV, the German
Josh,
organization.
we
Yeah.
can't see slides. Are you sharing slides with us, or we're just watching you, which is lovely? But if you're expecting to show some slides, you need to share them.
Oh, I share. Okay. Now we see
Okay.
on screen.
Now
we see the slide.
And now we see a slide. Now we see your front.
Okay.
Okay. That's
So,
Please.
yeah. So, okay. Greetings from Belgium. I'm a member of different organizations and amateur astronomer and a retired nuclear physicist. I have a remote observatory in San Pedro de Atacama at Space Ops by Alain Marie, who is also an amateur astronomer and very sophisticated observer of comets and asteroids. Yeah, San Pedro de Atacama is very touristic with, especially internet and at 2,500 meter elevation. And as you know, Chile has an exceptional number of clear nights. I'm there since 2011. The last 14 years, every year I observe between 312 and 345 nights. So the equipment I use is off the shelf, so I could buy it. I didn't develop anything. Actually, I have now two observatories. The one from August 2011 is equipped with a 40 centimeter telescope. And since beginning of the year, I have a C14 at f7. And both telescopes are on direct drive mounts. The one, the 40 centimeter is on a ASA DDM 85 from Astrosystem Austria. And the C14 is on a Nova 120 direct drive mount from France. Both scopes are equipped with CMOS cameras, QHY600M, and have photometric Astrodon filters in both cases. I use standard software, which at least is known to the amateur community on Windows, MaximDL, CCD Commander, and Leslie Photometry, which is the photometry program developed by a Belgian amateur. And to connect to the remote PC, I use VNC or AnyDesk. Yeah, the contribution of raw to images to BHDOM. I mean, this morning there was a presentation of Łukasz Wiercinowski, and which I actually got in contact in 2018, and since then I contribute to BHDOM. I was invited to participate in the Gaia Alerts workshop in Vipava in Slovenia, together with another Belgian amateur. We were the only two amateurs among the cloud of professionals. And it was actually the first conference where I was paid fully by, without myself paying. And actually, he mentioned, or Chris mentioned later on the image processing with CCT FOD. And in the last 2 weeks, since I'm in this list of email subscribers, 25,000 images were uploaded to BHTOM from Rode alone. And based on the Lucas presentation this morning, Rode images are in the order of more than 33% of BHTOM total images and counting, because actually 110 gigabyte of zip files are waiting to be downloaded to BHTOM. And actually, Przemek is doing that. And I asked him a couple of days ago whether he knows how many percentage contribution of Rode data are to BHTOM, and this was his answer. He was saying that it is at least 90%, which is actually a little bit too much, I would say. But he was giving me appreciation that the vast amount of homogeneous observations he could use to test many implemented procedures and for the development of CCT foot and BHTOM. So I appreciated that very much. This is an aerial view of Space Ops in Chile. So actually the owner is mainly giving tours in the night to tourists, and he has about 10 telescopes which he use for different objects in the southern sky to show to the tourists during presentations. And actually the biggest telescope he has installed is 1.15 meter, a Dobsonian of 1.15 meter. And down here you see the domes and roll-off sites where the remote telescopes are situated. And mine are the green and the red stars. And this is a nice picture some years ago, was taken by Yuri Beletsky of my telescope. It's situated in a clamshell dome which opens up because I do several stars simultaneously because I have a fast mount. In a normal dome, I would have already weared out the rollers and anything mechanically, and this just opens up. So, and here you have the nice Milky Way in at least in the summer period when the Chilean night sky are the longest. And now I don't show Gaia alerts, but other targets which I, in the meantime, have submitted to BHTOM. For instance, YSOs, so young stellar objects. I'm also participating in the so-called HOIS project, hunting outbursting young stars. And in Orion, in the Orion area, there are thousands of young stars, and T Orion is one of them. I have observations of more than 12 years, and you see it goes up and down by more than 2 magnitudes. And I have observations in 3 filters, BVI, B, V, and I, yes. And in recent years also R. Another object in Orion is TT Orion. Also there I have observations for the last 3 years. You see quite some staggering of the star is what the star is doing. Then, Assassin 24FW was mentioned just a few presentations back. I observed it as soon as I knew of this object, and you see that the star has been coming back to this normal brightness. And my observations show that there is not much variation so far in the bright state. And it was mentioned that there is also not much variation in the low state during the dimming event. And I'm part of the publication which was mentioned. And then also TISA Corona Borealis, I could observe from Chile. It's gone for the moment, but I also observe it from Belgium, from my backyard. I have another C14 in my backyard on a fast mount, so I observe every clear night. And actually this year I could already do that on 140 nights, which is exceptional for Belgium, because the weather in Belgium is not known to be very good. But nevertheless, T Corona Borealis is also on my program.
5 minutes, Josh.
Yes, S Doradus, a luminous blue variable in the Large Magellanic Cloud, I also observe since more than 13 years, and you see that it is going up and down, and has, I mean, the professionals which know about these observations, they don't really know what's going on with this star. And finally, a new contribution to which has been recently added to BH-TOM is a V348 Sagittarius, which is a hot RCRB star. I observe it since 12 years, and a professional astronomer from ARMAC Observatory in Northern Ireland stumbled across this data, and he was so excited that he invited me to give a presentation in his conference in 2018. And in the meantime, we have a paper on this. And you see that the star goes every year up and down, going from magnitude 12 in I down to magnitude nearly 19 in B. So highlights in road has been, I mean, since I'm a scientist, I always dreamed from having a paper in Nature. And as an amateur astronomer, I have in the meantime two. One was RR-SCO, the first white dwarf pulsar in Nature in 2016, and another one was Assassin 21QJ, the Nature paper in 23, which was here is the light curve. It goes dimmed for more than 600 days, and the conclusion was that it was a collision of two Neptune-sized planets. Okay. And also the ring system in V1400 CEN, which is J1407, was mentioned from SuperWASP, observed in 2007 or 2009. I'm observing it since I knew about this in 2011. It was said, yeah, in 10 years it will come back, but unfortunately it didn't come back yet. And but nevertheless, together with people from Leiden University, we have a couple of papers on this system. And then I mentioned it, cataclysmic variables. I have tons of data with and without superhumps. I always check Assassin and the time server whether there are interesting variables on cataclysmic variables. And and also symbiotic stars I observed for Ullis and Munari some years ago. And so far I have more than 140 publications with co-authorship, which can be found in the archive, searching for my last name, Hamsch. About 10 per year. So this is rather astonishing, because I know as a scientist that it takes time to get a paper published. In professional time, I never had 10 per year. So in conclusion, variable star observations open lots of possibilities for amateurs to contribute to scientific research. participation in alerts and requests for observations like AWSO assessing targets, Gaia alerts. And if you have an interesting target, just tell me and I will take it up into my observing session. And so far I've collaborated with many professional astronomers, which ended up in 140 plus refereed papers. And thanks to Presemec for uploading road images to PHTOP. Thank you very much for your attention, and this is my email address.
Thank you so much, Josh. That's really, really impressive. Continues to be really, really impressive. Before I open the floor up to questions, I'm going to ask you one. What is the field of view of your CCD?
It's the CCD now, the CMOS camera is a full frame 24 times 36 millimeter square size camera. Before I had a 36 times 36 square camera, CCD camera. I think the field of view is in the order of 40 times 30 arc minute.
So that's beautiful.
Lots of stars, yes, in the field.
I wonder if you or anyone has considered doing a deep dive into all the other objects, apart from the targets of interest that have been flagged, in especially the star-forming regions, to data mine and explore those objects.
Yes, I started because now software is available, also developed by Belgium amateur astronomers, which gives me the possibility, at least the known stars which are in the VSX, to also photometrize via the software. And yeah, in some cases, like in the Orion, there are 3,000 variables, and I have maybe 20,000 images. So that's 6 million photometric values. And actually, the AWSO has about 74 million contributions, and 14 million are from me. Be one out of 5.
Fantastic work. Thank you very much. We have a question from Michel Mayor. Go ahead, Michel.
Yes. Thank you, Joe. Very impressive. Transmit my greetings to Alamori, please.
Okay.
I have a question about Maxim DL, which you seem to be using regularly.
Yes.
We are using that for some professional telescopes, and there is a major drawback I find, that you cannot stop or interrupt exposure when there are clouds without losing it. I know you don't have much clouds in Atacama, but did you found that problem or?
I mean, I don't bother if there are clouds. I mean, since there are only a couple of nights where there are clouds. Okay, I mean, yeah, you saw during the presentation, for instance, in this big in this slide, there are some points up or down, and these are due to the fact that first of all, the star is very bright for a 40-centimeter telescope. And sometimes there are clouds passing, and then of course you have this kind of effect in the. So, but I mean, yeah, the professionals can discard those, and you have seen during the presentation of Chris for CCD FOT, he has shown images of road which he processed, and some of them were green. I mean, the most of them were green. Some of them were red, and this is due to some clouds passing. And yeah, I know that Maxim cannot be stopped. Yeah, but that's life. Yeah.
Thank you. We have a question online. Siegfried, would you like to ask it?
Yes, yes. What is your current limiting magnitude for useful photometry with the CMOS camera?
Actually, the CMOS camera is much more efficient than the CCD camera, except that the QE is actually shifted from the red into the blue. So it is more efficient in the blue and less efficient in the red. So I've seen that I can reduce my exposure times for most of the stars which I observe with the CCD and with the CMOS. With the CMOS, I can reduce them by a factor of 2. So yeah, when I started with the CCD, a certain object with 30 seconds, I can do the same now, the same quality with 15 seconds.
Okay,
But
and in terms
I have about 2,000 images per night for the moment.
okay, that's a lot.
Thank you, Siegfried. Good question. Was there one more? Did you spot? Przemek. No.
Michał Żejmo from Zielona Góra. I have a question about the configuration that you are using for this QHY 600 because we have this very similar camera in our observatory. So I wonder.
I mean, before I had an FLI CCD camera and I have an FLI filter wheel, which is very, very reliable and very much, I would very much recommend because it's driven by a chain, not by friction. Because yeah, I mean, I do yeah, as I said, I have 1,000 images per night, and I do continuous changing of the filter, and I mean, my first filter wheel had maybe 1.5 million turns, and then it broke. So just try this with a QHY filter wheel. It will wear out much earlier. So this is the combination of the CMOS and the filter wheel, and then it comes the telescope. I mean, and in the C14 case, it's there is a reducer which is giving a field of view in big enough for the CMOS camera. It's from a US company. It's the only reducer for a C14 which is giving you, for standard C14, which is giving you a big field.
Okay, thank you.
But there's nothing special.
Nothing special. I see one more question. We'll have one more question, please. Please wait for the microphone.
Hi, Staszek Zola, Jagiellonian University. I believe that Michał was also asking about the software setup of your CMOS. I would say since it is sort of...
I don't hear you. I mean, could you...
the mic.
Yeah.
The mic. My question is what you set up for CMOS, like gain, which gain, what is the reading mode?
Okay. I mean, I always do binning since the CMOS has 60 million pixels, and that would give you 120 megabyte of file size. And since I have, yeah, as I said, 2,000 images, that's a bit too much per night. And I do 4x4 binning, and the gain is 0, and the offset is 10.
Thank you very much.
The mode is,
Go ahead.
I think, mode number 3 or so.
Thank you. Please continue chatting on Slack to get the full details of the observing mode required. Let us thank Josh for an amazing talk.
Thank you.
And we're going to close. There will be an announcement, but let's thank all our speakers today for a really productive day. Thank you very much.
Now I have the mic so I can do the announcement. It's regarding tomorrow. Remember that we have a conference picture at the beginning of the coffee break. So who is not here is not on the picture. I think that's clear. So wear your nice shirts for that. But also don't forget that we are going for the take the trip directly from here. So, and it will be cold up there. So take nice shirts, but takes also the jackets because it will be cold. So we will have lunch, and directly after lunch, the bus will be departing from here. We'll go up and we'll return late. So, but anyway, up there it will be cold. And also, Anna is asking all the speakers from tomorrow to upload the presentation because we have almost 0 of them. So if you don't want to end up on the blacklist of Anna, then do that, please. Yes. Yes, I think that's the plan, no? That we will return here or to La Laguna, no? Yeah, all right. Yeah, no, definitely the bus will not go to Santa Cruz, but we can arrange probably that we'll kick out some people, you know, in La Laguna, but on the way there, we are not stopping anywhere. So if you are not here at the departure of the bus, you are staying here, not going if you don't have your own. Yes, yes, bus will be with us. Yes. All right. Enjoy your evening.